At the centre of the Milky Way, something is flickering in the dark. Sagittarius A is flaring like a heartbeat, and James Webb just watched it happen. Not a still, silent void, but a restless engine that shouldn't behave this way. So what did Webb actually catch? Harmless turbulence? Or an anomaly that could rewrite black hole physics and hint at what's coming for our galaxy? Every galaxy hides a private weather system, and ours is brewing around a 4 million sun mass abyss. What Webb uncovered is not a single spectacle, but a pattern that refuses to stay simple. To reach it, you don't fly inward, you translate the Milky Way into wavelengths the eye was never meant to trust. 26,000 light-years of dust stand between us and the core, turning starlight into silence, and leaving only infrared and radio to speak. That is where James Webb operates. Cold, shielded, patient, measuring changes so slight they look like noise until they repeat. But repetition is the beginning of danger, and the beginning of truth. In the galactic center, nothing sits alone. Gravity crowds the scene, magnetic fields braid through plasma, and shockwaves carve channels through clouds that should be calm. When headlines promise omens, the real threat is subtler, misreading the data and missing what the universe is teaching in plain mathematics. This documentary follows the evidence as it hardens from rumor into constraint. We will watch time itself become an instrument, because variability is a ruler. Each rise and fall sets a limit on how small, how fast, and how energetic the source can be. We will see why anomaly is not a jump scare word, but a signpost that a model has reached its edge, and we will ask the only question that matters beneath the drama. Are these signals the harmless turbulence of an underfed black hole, or a deeper clue about how galaxies grow and survive? The answer will not arrive as a single image, because the galactic center is not a portrait, it is a process. Along the way, the story widens beyond the horizon's immediate glow. The same region that feeds Sagittarius A also starves newborn stars, stretches filaments into impossible geometry, and moves gas through the core like a city's hidden infrastructure, quiet until it fails. Some of what we'll encounter will look engineered, almost intentional, until physics makes it stranger and more elegant than myth. We will keep one promise as we go: no prophecy, no supernatural warnings, no convenient apocalypse. Instead, we will build a case from calibrated light curves, spectra, polarization, and maps of cold gas, letting uncertainty remain visible rather than edited out. Because the terrifying part is not that the Milky Way has a monster at its center, it's that the monster behaves like a machine we can finally read, and the reading changes what we think black holes are for. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now settle in for a journey. We begin by crossing the dust barrier and dismantling the loudest claims, then follow the flicker into a wider architecture of fields, filaments, and flows. By the end, the anomaly becomes a blueprint, linking our galaxy's core to the engines that shaped the earliest galaxies. The headlines arrive first, louder than the science, and they arrive with the confidence of a siren. They promise an impossible sound from deep space, an apocalyptic timer, a signal that means the end. In thumbnails and clipped captions, the galaxy becomes a haunted house, every creak translated as a warning. What NASA actually receives is not audio, not prophecy, not a countdown hidden in static. It is light measured as numbers, shaped into light curves, spectra, polarization maps, and time variability. The signal is a stream of photons sorted by wavelength and time, then corrected for instrumental quirks and cosmic interference. The internet translates those graphs into fear because fear is easy to share and uncertainty is easy to weaponize. A plot with error bars looks like a secret, especially when the axes are unfamiliar. The real story is harder, and it is stranger, because it is testable. At the center of the Milky Way sits Sagittarius A, the compact radio source marking our galaxy's black hole. It is about 26,000 light-years away, buried behind the crowded disk and the luminous clutter of the inner bulge. If the Milky Way were a city at night, the center would be downtown, bright, busy, and almost impossible to see through the smog. That distance is not just a number, it is a time machine measured in years. The light we collect tonight began its journey when human civilization was still building its earliest cities. It crossed spiral arms, star-forming regions, and magnetic storms, then arrived as a faint, heavily filtered whisper. Between us and that centre lies a thick lane of dust and gas that blocks visible light. Optical telescopes can point at the right coordinates and still see almost nothing useful. The view is not empty, it is simply obscured. Like trying to read a sign through a sandstorm, dust grains are sized to scatter and absorb short wavelengths efficiently, and that size relationship matters. Visible photons interact strongly with grains comparable to a fraction of a micron, so starlight is redirected, dimmed and reddened. The energy does not vanish. It warms the grains and returns as infrared glow. In visible light, the galactic centre is not a dramatic silhouette. It is a blank patch where information is missing. The sky looks ordinary, but the physics is not. Behind that darkness, stars orbit at hundreds or even thousands of kilometers per second. Infrared light has longer wavelengths that slip between grains more easily, and that is the basic reason the center becomes reachable. Change the color of your vision, and the dust becomes less like a wall and more like a curtain. You still lose some light, but you regain structure, motion, and context. James Webb was built for that change, and its design is a statement of intent. A gold-coated mirror gathers faint infrared photons, while a sunshield the size of a tennis court keeps the telescope cold enough to avoid blinding itself. In space, heat is noise, and Webb was engineered to quiet that noise. Its near and mid-infrared instruments can look through the obscuring veil and still separate fine structure. That separation is not cosmetic, it is quantitative. It means crowded star fields become resolvable, and faint variations stop being smeared into the background. NIRCam captures near-infrared detail where stars and hot gas dominate, and where extinction is already dramatically reduced. In those bands, the galactic center's stellar population emerges as a dense swarm, each point a sun with its own spectrum. The images are not calm, they feel like a living metropolis of light. Miri extends to mid-infrared, where warm dust, molecules, and cooler structures reveal their signatures. Here, the scene changes texture. Filaments, knots, and glowing lanes trace where radiation heats grains and where chemistry survives. The mid-infrared is a map of environments, not just objects. This is not a single telescope story, because black holes do not speak in one band. The galactic center is a multi-wavelength puzzle that only resolves when different observatories overlap. Each wavelength is a different diagnostic, and each diagnostic answers a different kind of question. ALMA watches millimeter and submillimeter emission from cold gas and dust, the raw material of future stars. It traces molecular clouds by their rotational lines, revealing temperature, density, and motion. When you watch those lines shift, you see gas streaming, colliding, and shearing under gravity. Chandra and XMM Newton watch X-rays from the hottest plasma and the most violent particle acceleration. They catch flares that signal sudden energy release close to the event horizon, where magnetic fields and gravity compete. In X-rays, the galactic center stops being dusty and becomes sharp, energetic, and unforgiving. The Event Horizon Telescope adds a different kind of sight, built from synchronization rather than a single mirror. It links radio dishes across Earth to reach horizon-scale resolution, turning a distant shadow into a measurable shape. The technique is interferometry, but the effect feels like teleportation, an Earth-sized eye staring at a region smaller than Mercury's orbit. Together, these instruments turn Sagittarius A from a metaphor into an object with constraints. They let us compare models to data and discard the ones that fail. In astronomy, you rarely touch the subject, so you interrogate it with consistency across wavelengths. The monster itself is not a mythic devourer, even if the name invites superstition. Sagittarius A is a black hole of roughly 4 million solar masses, compact enough that its gravity dominates the central region. Its mass is known because stars near the center trace precise ellipses around an unseen focus. That measurement was not instantaneous, and it has a history of patience. Over decades, teams tracked individual stars, especially the famous S-stars, watching them complete orbits in human lifetimes. When one star swings through its closest approach, the data becomes a verdict. A black hole is defined by an event horizon, a boundary where escape becomes impossible once crossed. The horizon is not a surface you crash into, and it is not a trapdoor in space. It is a geometric limit set by space-time curvature, and it marks where paths outward simply stop existing. Outside that boundary, gravity follows the same inverse square rules as any mass, and that fact is often forgotten. A black hole's pull at distance depends on mass, not on the drama of its name. Replace Sagittarius A with 4 million suns spread out the same way, and Earth would feel the same net attraction. That is why black holes do not suck like vacuum cleaners from across space despite the popular image. At Earth's distance, Sagittarius A pulls no harder than the same mass in stars would. The Milky Way's disk, halo, and dark matter shape our orbit far more than the central horizon does. The danger is not the label, but the proximity, where gradients become lethal. Get close enough and tides, radiation, and orbital energy loss can tear matter apart. The difference between safe and destroyed is not moral, it is mathematical. Matter rarely falls straight in because angular momentum is stubborn and conserved. Gas arrives with motion, so it circles, collides, and settles into an accretion flow that heats, magnetizes, and radiates as it spirals inward. Friction here is not like rubbing hands, it is turbulence and magnetic stress converting motion into heat. In that flow, magnetic fields twist and reconnect, and electrons can be driven to relativistic speeds. Those processes produce flares and flickers that telescopes can time, sometimes minute by minute. When reconnection snaps field lines into new configurations, stored energy becomes light with startling efficiency. Some of that light is synchrotron emission, produced when fast electrons spiral around magnetic field lines. It is polarized, meaning the light carries an imprint of field geometry. Polarization is not decoration. It is a compass pointing to the invisible structure shaping the plasma. For decades, Sagittarius A was described as quiet, even dormant, especially compared to quasars. Quasars blaze because their black holes are fed by dense, sustained inflows, often triggered by galaxy interactions. They turn gravity into radiation with such power that they outshine their host galaxies. Our galactic center seemed starved by comparison, and the numbers supported the impression. It radiated weakly, and many models treated it as a low-activity baseline for black hole physics. The quiet was useful because it suggested a simpler laboratory, less glare, fewer complications. Yet the cosmos rarely stays quiet forever, especially in a region as crowded as the inner parsecs. The Milky Way's center is packed with stars, gas streams, and turbulent magnetic structures that constantly rearrange. Stability there is not a default state, it is a temporary compromise. Even a small change in inflow can change the light, because the inner flow responds quickly. Even a brief reconnection event can release energy faster than human intuition expects. When the timescales are minutes, the emitting region must be compact, and compact regions are sensitive. The observational challenge was always the same, and it shaped what we believed. We could infer motion from stellar orbits, but the immediate environment of the black hole stayed blurred and hidden. The physics we wanted was happening where dust and crowding were at their worst. Astronomers tracked stars whipping around an unseen mass, proving the black hole's existence with precision. That triumph still left a gap between knowing and seeing, between a dynamical measurement and a direct view of the engine. In science, gaps become invitations for speculation. The gap was dust, and dust shaped the narrative in subtle ways. If you cannot watch the center directly, you assume steadiness, and you miss the short-lived events. A flare that lasts half an hour can vanish between observing campaigns and leave no story behind. Webb's promise is not that it will find a monster, but that it will remove excuses. With infrared sensitivity and stability, it can monitor the center repeatedly and consistently. Consistency matters because variability is not a single event, it is a pattern. Repeated monitoring changes the kind of questions you can ask, and it changes what counts as evidence. Instead of asking whether Sagittarius A is active, you ask how it varies minute to minute. You ask whether the flickers have preferred timescales, and whether those timescales drift. Time variability is where the physics hides, because timescales translate into sizes. A flare's rise time limits the size of the emitting region, because light cannot cross a larger region that quickly. If brightness doubles in minutes, the source cannot be larger than a few light minutes across. Spectra reveal temperature, composition, and particle distributions, and they show whether emission is thermal or non-thermal. A smooth continuum can point to synchrotron processes, while lines and features can reveal molecules and dust chemistry. Spectroscopy is the difference between a photograph and a diagnosis. Polarization reveals magnetic field geometry, and geometry is the language of accretion flows. A changing polarization angle can imply a rotating hotspot, a shifting field, or a turbulent cascade. When multiple instruments agree on that change, the interpretation gains weight. This is how discovery pipelines work, and the pipeline is less glamorous than the rumor. They turn photons into calibrated measurements, then into models, then into arguments that can be checked by other teams. The chain includes bias corrections, background subtraction, and careful accounting of uncertainty. The terrifying anomaly headlines skip that chain, because the chain is slow and the market is fast. They treat a plot as a message, and they treat uncertainty as evidence of conspiracy. But uncertainty is not a flaw. It is the honest boundary of what the data can support. The real stakes are bigger than any jump scare. The Galactic Center is the closest extreme laboratory for gravity, plasma physics, and star formation under tidal stress. It is where theories of accretion and feedback can be tested without crossing intergalactic distances. It is extreme because everything is packed together, and proximity changes behavior. Stars orbit fast, gas streams collide, and radiation fields are harsher than in the calm outer disk. The region feels crowded even in data. Bright sources overlap and the background glows with unresolved light. It is also extreme because the black hole sets a deep gravitational potential that warps trajectories. Orbits precess, gas shears, and the difference between stable and unstable can be a small perturbation. A cloud that would drift peacefully elsewhere can be stretched into a filament here. Studying this region is not about fearing an attack from space, because physics does not aim. It is about learning how galaxies regulate themselves, and how black holes grow without always shining like quasars. If quiet black holes still flicker, then dormant becomes a misleading word. If Sagittarius A can switch states, it becomes a template for dormant black holes elsewhere, hidden in ordinary galaxies. If it cannot, the models must explain why our center is different, despite similar masses and similar physics. Either outcome sharpens our understanding. Webb enters this story at a moment when the tools finally match the questions, and that timing matters. The EHT gave us a horizon-scale silhouette, but not continuous infrared behavior. It showed shape and scale, yet left the day-to-day temperament unresolved. X-ray observatories see the hottest flashes, but their photon counts can be sparse when the source is faint. ALMA maps cold gas, but it does not always capture the fastest inner changes. Each instrument excels in its domain, and each domain has blind spots. Webb bridges crucial scales, sitting between the cold reservoir and the hottest outbursts. It can track infrared emission, where synchrotron and thermal components overlap, and where dust extinction no longer dominates the view. That overlap is where competing models diverge, and where observations can choose. This is where the documentary draws a line between sensationalism and space facts, and the line is methodological. The real strange is not a sound in a vacuum, but a plasma that brightens without warning. The real drama is not supernatural, it is electrodynamics under extreme gravity. The real danger is not a countdown, but a physical process that converts magnetic stress into radiation in minutes. The real mystery is what triggers those releases, and why some events stay small while others flare. Is it a threshold in turbulence, a sudden infall, or a geometric alignment we barely catch? We also have to widen the frame beyond the black hole itself, because the environment writes part of the script. The Galactic Center hosts star formation in harsh conditions, where tides can both compress and disrupt clouds. It is a place where gravity can nurture and shred in the same orbit. Massive stars live fast and die violently there, enriching the environment with winds and supernova debris. That feedback can starve or feed the central accretion flow, depending on how it stirs the gas. A wind can clear a cavity, but it can also drive shocks that pile material into denser streams. Every component interacts, and the interactions are the point. Gas dynamics set the fuel supply, stellar populations set the turbulence, and magnetic fields set the efficiency of energy conversion. The center is not a single object, it is a coupled system with many clocks. So the central question becomes concrete, and it becomes measurable. What did James Webb actually reveal about Sagittarius A and its neighborhood, and what does that imply about black holes as engines? When a source flickers, does it reveal a rotating structure, a changing inflow, or a magnetic heartbeat? Does the new variability signal a genuine threat to Earth, or only a deeper clue about how galaxies evolve? If there is a threat, it must be quantified, not imagined. At 26,000 light-years, even powerful outbursts dilute, and geometry determines what reaches us. At that distance is a shield, but it is not an excuse to ignore physics. Understanding the centre helps us understand what the Milky Way has been and may become. The past activity of Sagittarius A is written faintly in surrounding gas, and the present activity is written in flickers. The story begins with a journey through dust, because dust is what kept the centre mythic for so long. Infrared turns that myth into a dataset that can surprise us, and it turns absence into detail. With each band, another layer of the curtain lifts, and the first surprise is simple and unsettling in its clarity. Webb does not see a sleeping giant, it sees constant motion where we expected stillness. The centre breathes in light, brightening, dimming, and shifting, as if the engine is always idling. From here, we move from the gate to the engine. We follow the flickers and flares toward the anomaly that the headlines distorted, and the measurements finally define. What looked like an omen becomes a curve, and the curve becomes a question the universe can answer. From the gate of dust and distance, the story narrows to time. The camera does not simply stare at Sagittarius A and take a portrait. James Webb watches it, patiently, continuously, long enough for randomness to reveal its hidden rules. It is a different kind of attention, closer to listening than looking, because the signal is written in change. In the mind's eye, the galactic centre is never a clean target, and that messiness is physical rather than poetic. It sits behind curtains of interstellar dust, micron-sized grains of carbon and silicates, that swallow visible light and scatter detail into haze. Near-infrared wavelengths slip through that dust more easily, so the core emerges as a crowded amber-lit field. Stars pack the frame like grains of salt on black velvet, and some are so bright they bloom into soft halos. Yet the black hole itself remains invisible, because an event horizon does not reflect or glow. What Webb measures is the glow of matter that dares to orbit close, where gravity is steep and time feels compressed. The setup is deceptively simple, but the discipline behind it is strict and almost monastic. NIRCam locks onto the galactic centre and records a near-infrared light curve for roughly 48 hours. The goal is not a single perfect frame with heroic sharpness, polished for a poster. The goal is an uninterrupted time series that does not miss the briefest outbursts, even if those outbursts look like mere tremors. That requirement sounds mundane until you remember what usually goes wrong, and how often astronomy must negotiate with the planet itself. Telescopes on Earth lose the target to daylight, weather, and atmospheric turbulence that makes stars shimmer and blur. Even when skies are clear, the air glows faintly in infrared, adding a shifting background that must be subtracted. So the story becomes chopped into pieces, and the gaps masquerade as calm. Even space telescopes often schedule observations in short blocks, because time is scarce and competition is fierce. Webb in this campaign commits to continuity, an observational luxury that turns flickers into evidence. Unbroken monitoring changes what counts as proof, because it changes what you can safely infer. If you sample once per night, you can fuse gaps with quiet and coincidence with rhythm. If you watch continuously, you measure how often flares occur, how fast they rise, and how their colours evolve. You also learn what quiet really means, because quiet is not the absence of activity. Quiet can be a steady crackle that only looks smooth when you average it away, the way a distant waterfall seems still. Time domain astronomy is a discipline built on impatience, yet it demands endurance and a tolerance for long stretches of ambiguity. It treats brightness as a moving target rather than a static property pinned to a catalogue. In that mindset, variability is not noise that contaminates the measurement. Variability is the signal that carries the physics, because the engine reveals itself when it cannot hold steady. Astronomy has a long history of learning this lesson the hard way, and the milestones are written in pulses and eclipses. Pulsars were first recognised as repeating radio flashes, not as objects with a particular colour in a photograph. X-ray binaries revealed their nature through bursts, dips, and orbital shadows, not through a single spectrum taken at leisure. Even the first hints of black holes in stellar systems came from motion and change, because the dark object itself refused to shine. Sagittarius A belongs to that tradition, where time is the instrument that makes the invisible measurable. Sagittarius A has long been called quiet, and the label is understandable in a universe that contains true beacons. Compared with quasars that blaze across the cosmos, our central black hole is underfed and dim. Its accretion rate is tiny compared with the theoretical maximum, and much of the infalling energy never becomes light. Yet quiet compared with quasars is still a dangerous phrase because it smuggles in a false picture of rest. Webb tests that label by asking a sharper question. Does the black hole ever truly rest? The answer arrives as a pattern with no pattern, like weather seen from above where fronts form and dissolve. The infrared emission flickers constantly on seconds to minutes timescales, and the baseline never settles. Small pulses stack on top of each other like boiling water, where bubbles rise, burst and vanish. Then, without warning, the light leaps into major flares that dominate the curve. The effect is not a single drama, but a persistent nervous system of light. On screen, the light curve becomes a heartbeat that refuses to settle into a calm rhythm. The baseline jitters, never flat, as if the source is breathing in tiny sips. Peaks rise sharply, then soften and slide back down, sometimes with shoulders and substructure that suggest multiple injections of energy. It is not a single flare shape repeated like a stamp. It is a family of events, related but not identical, as though the engine improvises within constraints. Webb sees powerful events several times a day during this campaign, and the repetition itself is the shock. The reported rate is roughly 5 to 6 major flares per day across the 48 hours. The exact count matters less than the implication that follows, because the curve leaves little room for true downtime. The engine is active often enough that between flares becomes a slippery phrase. There is no neat periodic clock hiding in the data, and that absence is as informative as any peak. The flares do not arrive at a fixed interval that would suggest one orbiting beacon, like a lighthouse sweeping past. The variability is stochastic, shaped by turbulence and chance alignments, yet still constrained by physics. Random does not mean lawless, because the laws show up in distributions, delays, and limits. The question becomes statistical. What kinds of randomness can a black hole produce? This is where the word disk can mislead, because it carries a comforting image of order. The environment is not a flat ring like Saturn's, with tidy edges and a single plane. Sagittarius A is surrounded by a hot, magnetized, turbulent accretion flow that is thick, messy, and constantly rearranging. The structure is more like a churning, puffed-up torus than a thin vinyl record. In visual terms, it is a storm cloud of plasma, not a polished wheel. The reason is partly starvation, and the physics is brutally practical. When a black hole is well fed, a thin disk can radiate efficiently and shed heat, so it collapses into a flatter shape. When it is underfed, the gas struggles to cool, so it stays hot and inflated. Heat becomes pressure, pressure becomes thickness, and thickness becomes chaos. In plain terms, the flow is too energetic to lie down, and too thinly supplied to settle. Gas near the black hole does not drift gently inward, like smoke toward a drain, because angular momentum is a stubborn thing. It orbits at significant fractions of light speed in the inner region, where the gravitational well steepens dramatically. Collisions, shear, and magnetic stresses convert orbital energy into heat and particle acceleration. The flow becomes a laboratory for extreme plasma physics, built from ordinary matter pushed into extraordinary conditions. Even the concept of friction is replaced by magnetic turbulence that transports angular momentum outward. Close to the event horizon, gravity sets brutal timescales that no narration can soften, because the clock is built into space-time. If brightness changes in minutes, the emitting region must be compact. Light travel time alone limits the size, because a region cannot coordinate a rapid change faster than light can cross it. That simple constraint turns flickers into a ruler, and it works even when the source is unresolved. For Sagittarius A, that ruler is especially powerful because we know its mass well, and the measurement has a history. Stellar orbits around the galactic center have been tracked for decades, with stars like S2 tracing tight ellipses that point to an unseen mass of about 4 million suns. With that mass, a gravitational radius becomes a concrete scale, not a metaphor. Minutes of variability correspond to only a few gravitational radii, a neighborhood where relativistic effects are not optional details. In that neighborhood, even the direction of time feels like part of the machinery. The accretion flow is plasma, not ordinary gas, and that difference is decisive at every step. Electrons and ions move in electromagnetic fields that they also generate, so motion and magnetism are inseparable. Magnetic field lines are dragged, twisted, and braided by the churning motion, as if the flow is kneading invisible threads. The field becomes both a scaffold and a spring, storing energy in its geometry. In a plasma, the field is not decoration, it is part of the dynamics. In visuals, imagine translucent streamers of light wrapped around an invisible drain, with knots that brighten and fade. They stretch, kink, and snap back, as if the flow is testing its own magnetic fabric. The black hole is not pulling on field lines directly because field lines are not physical cords. The plasma drags them, and the plasma is what gravity commands. Gravity sets the stage and magnetism writes the choreography. When field lines tangle, they store energy in tension, like a rubber band twisted too far and held in place. When the configuration becomes unstable, the lines can snap and reconnect, changing partners in a sudden topological reshuffle. Magnetic reconnection is the release valve that makes the stored energy available. It converts magnetic energy into heat, bulk motion, and fast particles. In the language of physics, it changes magnetic topology and dissipates energy in a compact region. A useful analogy is solar flares, scaled to a harsher arena where the margins are thinner. The sun reconnects field lines in a relatively gentle gravitational field, and we can watch the aftermath in ultraviolet loops. Near Sagittarius A, reconnection happens in deeper gravity, higher temperatures, and stronger orbital shear. The same physical process plays out, but the stage is smaller and the stakes are higher. The flare is the visible signature of a magnetic system losing its balance. Reconnection is not a special effect invented to decorate a story about black holes, and it is not confined to astrophysics. It is a known plasma process that appears in laboratories, in Earth's magnetosphere, and in the solar wind. Spacecraft have flown through reconnection regions near our planet, measuring particle jets and magnetic flips directly. That matters because it anchors the story in measured physics, not speculation. Webb's contribution is that it watches the process where conditions are extreme and the geometry is compact, and where the consequences unfold in minutes. Yet the story is not just reconnection happens, because that would be too easy and too vague. The question is how reconnection behaves in a relativistic, turbulent flow where gravity warps trajectories and time. In that regime, the plasma is hot enough that particles move fast even before they are accelerated. The magnetic field can be strong enough to guide motion tightly, even as turbulence tries to tear order apart. The flare becomes a probe of competing influences: shear, turbulence, and magnetic tension. The flare light implies relativistic electrons, and that phrase is more than dramatic language. These particles are accelerated to near light speed and forced to spiral around magnetic field lines. Spiraling charges emit synchrotron radiation, which naturally lands in the infrared for plausible field strengths and electron energies. The emission is polarized in characteristic ways, and it carries fingerprints of the magnetic geometry. Even without resolving the source, the spectrum and timing hint at the field's strength and structure. Synchrotron emission also comes with a built-in clock that nature cannot easily hide, because radiation drains energy at a predictable rate. High-energy electrons radiate more powerfully and cool more quickly, because their energy loss scales steeply with both energy and magnetic field. As they lose energy, the characteristic emission shifts to longer wavelengths. That shift is a prediction, and Webb can test it with timing rather than guesswork. The flare is not only bright, it is aging in real time. The key measurement is simultaneous emission at about 2.1 microns and 4.8 microns, captured as the same event unfolds. NIRCam can track both bands, letting astronomers compare the timing of peaks within the same flare. This matters because it removes a common ambiguity in astronomy. You're not comparing different nights or different instruments with different calibrations. You're watching the same event, split into two colors, as it unfolds. The data becomes a controlled experiment performed by nature. In the data, the shorter wavelength rises and peaks first, then the longer wavelength follows with a delay. This is not a trivial detail that can be waved away as instrumental noise, because it repeats across events. It is a direct hint that the electron population is evolving in real time. The flare is not a static lamp that turns on and off. It is a changing distribution of particle energies, cooling and reshaping as it radiates. The light curve is telling you that the plasma is not merely bright, it is transforming. One interpretation is cooling, and it is physically straightforward in the way good diagnostics often are. The flare begins with a burst of very energetic electrons that radiate strongly at shorter wavelengths. As those electrons lose energy through synchrotron losses, the emission shifts toward longer wavelengths, so the 4.8 micron light peaks later. In plain terms, the flare reddens as it fades because the particles are running out of punch. The lag becomes a stopwatch for energy loss. Another interpretation adds expansion, and it changes the geometry without changing the basic logic of spectral evolution. A compact blob of plasma can expand after reconnection, lowering particle energies and magnetic field strength as it grows. Expansion also pushes the emission to longer wavelengths and stretches the flare in time, because the system's characteristic frequencies slide downward. The light curve becomes a record of an outflowing, decompressing packet of plasma rather than a fixed hotspot. In visuals, the bright knot swells and cools, like a spark turning into a fading ember. Either way, the delay becomes a constraint that models must respect, and constraints are where mystery becomes mechanism. Theories must reproduce both the amplitude and the timing between bands, not just one or the other. A model that matches the brightness but misses the lag is incomplete. A model that matches the lag but cannot produce the observed power is also incomplete. The data demands coherence, not just plausibility. This is how chaotic light becomes a laboratory, even when the source cannot be resolved as an image, and never will be in these wavelengths. The light curve is not just a record of excitement for a press release. It is a dataset that limits magnetic field strength, particle acceleration efficiency, and the size of the emitting region. It also constrains how quickly energy can be injected and how quickly it must be lost. In effect, Webb is measuring the black hole's metabolism. The flickering background matters as much as the big flares, because it defines the system's default state and its baseline physics. Continuous low-level variability suggests constant small reconnection events, or persistent turbulence that never fully relaxes. The accretion flow behaves like a bubbling surface, where tiny releases happen all the time. If you only looked for the largest peaks, you would miss the fact that the engine never stops simmering. The quiet state is not silence, it is a low roar. Major flares may be the tail of the same distribution, not a separate species of event with a different cause. They might be rare, large reconnection episodes in a system that is always reconnecting somewhere. That idea links the quiet and the loud into one physical picture, which is exactly what a good theory should do. It also echoes what we see on the Sun, where microflares and major flares may share underlying statistics. The difference is scale and environment, not the underlying grammar of plasma. The unpredictability is itself informative, and it carries a subtle message about structure in the inner flow. If flares were strictly periodic, a single orbiting hotspot would dominate, and the clock would be easy to identify. The observed randomness points instead to a turbulent flow with many active regions, each with its own brief life. The black hole's neighborhood behaves less like a machine and more like weather. And weather, while unpredictable in detail, is not beyond physics. This does not mean the system is unknowable, because turbulence has statistics even when it lacks a schedule. Over 48 hours, Webb can measure flare frequency, typical durations, and the distribution of energies. It can also measure how often small flickers cluster into larger events, hinting at cascades in the magnetic field. Those are the kinds of clues that let theorists test whether their simulated chaos resembles the real thing. The question becomes whether the model produces the right kind of disorder. Those statistics can be compared to simulations of magnetized accretion flows, which have matured for decades and now include relativity as standard equipment. In particular, general relativistic magneto-hydrodynamic models predict how magnetic fields amplify, how plasma heats, and how reconnection might occur near the horizon. They also predict how Doppler boosting and gravitational redshift can modulate observed brightness. Even when the underlying physics is local, relativity shapes what the telescope receives. A flare's apparent intensity can be boosted or dimmed by motion, as well as by intrinsic power. In such simulations, magnetic fields can be amplified by turbulence and rotation through dynamo-like processes, building structure out of disorder. The flow can develop magnetically dominated pockets, where reconnection becomes likely and sudden. The plasma can become too temperature, with ions hotter than the electrons, which changes how efficiently it radiates in different bands. Each of these details affects the light curve, so timing becomes a way to choose between competing assumptions. The light curve is not merely a graph, it is a filter that rejects bad physics. Webb's light curves become a test of those models, and the test is unforgiving because it is multidimensional. If the simulated flow produces too few flares, the reconnection rate may be wrong, or the turbulence may be too weak. If the simulated flares cool too quickly, the magnetic field strength or particle injection may be misestimated. If the simulated lags between wavelengths are absent, then the electron evolution is being modelled incorrectly. The data does not demand perfection, but it demands the right relationships. The result is a new kind of constraint on the central question, and it is more precise than a label like quiet. What did Webb actually reveal about Sagittarius A? It revealed that even a low-feeding black hole can be continuously active in infrared, with energy release happening on human timescales. The centre of the Milky Way is not a static monument. It is a system in motion, always rearranging itself. The surprise is not a single flare, it is the persistence. The phrase terrifying anomaly needs a checkpoint here, because drama can distort meaning if it is left unexamined. There is no supernatural signal hiding in the flickers, and there is no coded message riding on the peaks. The anomaly is that nature refuses to be tidy, even when we label a black hole dormant. The surprise is not that physics breaks. The surprise is that physics is busy, and it is busy in a place we once imagined as inert. The terror is intellectual, and it is the kind that science often delivers when it takes away a comforting simplification. It is the realization that the simplest picture of a quiet center was incomplete, perhaps even complacent. The engine is not off. It is idling, sputtering, and occasionally roaring, driven by plasma physics under extreme gravity. If the nearest supermassive black hole behaves like this, what does that imply about the countless others we cannot watch so closely? How many quiet nuclei are quietly crackling, just beyond our current patience? This matters beyond our galaxy, because microphysics scales upward, even when environments differ and feeding rates change. The same processes that accelerate electrons near Sagittarius A should operate near other black holes, from stellar mass systems to quasars. Distant quasars are too far for this level of timing detail, and their inner regions remain unresolved. Yet their models rely on the same assumptions about magnetic fields, particle acceleration, and radiative cooling. If those assumptions are wrong in our backyard, they are wrong everywhere. If Webb measures time delays between wavelengths in our nearest supermassive black hole, those delays calibrate the physics in a way that theory alone cannot. They tell us how quickly electrons cool and how magnetic fields shape emission in a realistic environment. That calibration can be carried into quasar models where direct tests are impossible. It becomes a bridge between a nearby laboratory and the deep universe. In a field built on inference, a nearby constraint is priceless. Cosmology depends on those models more than headlines admit, because black holes are not isolated curiosities that merely decorate galaxies. Black hole growth influences galaxy evolution through feedback, shaping gas reservoirs and star formation histories over billions of years. If accretion flows are more variable than assumed, then average luminosities can hide bursts that matter for heating surrounding gas. A galaxy can remember a black hole's outbursts even when the black hole looks quiet today. The past can be written in temperature, ionization, and motion. A black hole that flickers changes how we interpret its history, and the Milky Way offers hints of that history in its surroundings. The galactic center contains structures that look like echoes of past activity, written into gas and dust on larger scales. Understanding today's flare physics helps decode those fossil signals, because it tells us what kinds of outbursts are natural. It also tells us what energy budgets are plausible when the black hole is underfed. The present becomes a key to the archive. The 48-hour campaign also reframes risk, and it is worth stating plainly because fear loves vague numbers. Variability does not equal threat, and flares are not a countdown. At 26,000 light-years, even strong flares are diluted by distance, and Sagittarius A is not aimed like a weapon. The radiation we see is a diagnostic, not a hazard. The danger is not physical, it is interpretive. The real question is not whether Earth is in danger, because the geometry and the distance make that fear misplaced. The real question is what these flares reveal about how black holes eat when they are underfed. The Milky Way offers a nearby case study of low-level accretion that may be common in the universe. Most black holes, most of the time, are not quasars, so this regime may be the rule rather than the exception. If so, then flickering is not an oddity, it is a baseline behaviour. Webb's monitoring is a reminder that proximity is power, and that time can substitute for spatial resolution when the source is too small to image. We cannot resolve the event horizon directly in infrared, yet timing lets us infer scales. Minutes correspond to light minutes, and light minutes correspond to only a few gravitational radii for this mass. That connection ties the light curve to the horizon with a chain of simple constraints. The graph becomes a map, drawn in time rather than space. When the brightness changes quickly, the action must be close, because the emitting region cannot be enormous. The bubbling disk is not a distant ring whose changes take hours to communicate. It is the inner flow, where space-time curvature is strongest and magnetic fields are most stressed. In that region, a small rearrangement can produce a large observational consequence. A slight twist in magnetic geometry can become a flare that crosses interstellar space and reaches a telescope at L2. The chapter's core revelation is continuous activity, and it reshapes the narrative tone without changing the facts. Sagittarius A does not switch on only for special occasions, and it does not wait for human attention. It produces a constant shimmer of small events and a steady cadence of larger flares, with no predictable schedule. The black hole is not a sleeping monster. It is a restless engine whose restlessness is measurable, and measurement, not metaphor, is what turns unease into understanding. The physics behind the shimmer is not mystical, even when the visuals feel otherworldly and the language strains for images. Turbulence amplifies fields, and rotation twists them into stressed configurations. Reconnection releases energy in bursts, and those bursts accelerate electrons into relativistic motion. Relativistic electrons radiate synchrotron light and then cool, shifting the emission from shorter to longer wavelengths as the flare evolves. The story is dramatic because the conditions are extreme, not because the rules are unknown. The measurement that anchors this story is the lag between 2.1 and 4.8 microns, repeated across flares like a refrain. It turns a dramatic flare into a diagnostic of particle energy loss, which is a quantitative statement rather than a metaphor. It also turns a rumour about an anomaly into a constraint that models must satisfy. In science, that is the difference between a mystery and a mechanism. And mechanisms, once found, can be compared across the universe. This is the moment where the documentary tightens its focus, because the data forces a specific interpretation rather than a vague mood. The monster is not sleeping, but it is not awakening into apocalypse either. It is behaving like a real accreting black hole, governed by equations that can be tested. The fear dissolves into a sharper kind of awe, the awe of a system that is complicated but not arbitrary. The flicker becomes a signature, not a threat. And the test is not finished because near-infrared flares raise the next question, with almost mechanical inevitability. If the inner flow is this active in infrared, what should happen in mid-infrared and in X-rays when the most energetic particles appear? Do the biggest events produce hotter components that Webb cannot see in these bands? Do they leave signatures that connect infrared flickers to high-energy flashes? If the infrared is the ember, where is the flame? From here, we move from flickers to expectations. We follow the energy upward in wavelength and temperature, looking for signatures of hotter plasma and more violent acceleration. The next chapter asks whether Webb's view is only the beginning of a broader storm. From flickers to expectations, the story climbs the energy ladder and waits for escalation. In the near-infrared, Sagittarius A rarely sits still, and that constant glitter trains the mind to anticipate a bigger turn. When a source crackles all day at a few microns, the next question feels inevitable. Does the engine sometimes tip into a hotter, harder state? Does the Milky Way's center ever resemble an active galaxy? Not just in metaphor, but in measurable physics. The fear is not irrational, because the universe has shown this pattern before, often and at enormous scale. Many galactic nuclei spend long eras dim, then surge when fuel arrives in quantity and stays long enough to reorganize the flow. When accretion rates rise, disks brighten, coronary heat, and jets can form with little warning because magnetic fields respond quickly to new conditions. In the extreme, a quasar phase can outshine an entire galaxy for millions of years, turning a quiet spiral into a beacon. Historically, that realization reshaped astronomy in the 1960s, when quasars were first identified as distant compact powerhouses rather than odd nearby stars. Visually, the comparison is stark and the documentary leans into it. A quiet spiral galaxy looks like a city at night, with soft starlight and dark lanes of dust cutting across the glow. A quasar host, by contrast, is a searchlight in the cosmic fog, its nucleus so bright that the surrounding stars become background texture. In some images, the core blooms into a saturated white, and the galaxy's arms look like faint brushstrokes around a welding arc. That is the ladder the audience imagines, and Sagittarius A sits at the bottom rung, close enough to study but far from that blinding regime. Sagittarius A is not a quasar today, yet its constant flaring invites a dangerous narrative. Viewers hear 5 or 6 major flares per day and imagine a ramping sequence, like a machine warming up through repeated cycles. They picture a threshold being approached, where each flare primes the next with leftover heat, leftover turbulence, and leftover magnetic tension. They ask whether the Milky Way's centre is rehearsing for an awakening, and whether those rehearsals are getting louder. It is a natural story to tell because the human brain treats repetition as a prelude, even when nature is simply stochastic. That intuition has a scientific echo because accretion flows do change states in other systems. In stellar mass black holes, X-ray binaries flip between soft and hard modes as the inflow geometry reorganizes and the dominant radiation mechanism changes. Those transitions can be dramatic because a small shift in density or magnetic structure can alter how efficiently energy becomes light. The same physics scales upward because gravity is scale-free and the equations do not care whether the black hole is stellar or supermassive. In some active galactic nuclei, long-term brightening tracks changes in supply, viscosity and magnetic topology, and the nucleus can stay elevated for years. The question is whether our black hole is merely flickering, or actually shifting regime in a way that would matter. To test that fear, astronomers need a wavelength that sits between ember and flame. Near-infrared traces hot electrons and fast synchrotron changes close to the hole, where magnetic fields can be intense and orbital times are short. X-rays trace even hotter plasma and the most energetic particle populations, where the physics becomes unforgiving and radiative processes are less ambiguous. Mid-infrared sites in the middle, sensitive to cooler components and different emission regimes, and it can reveal whether a flare's energy spreads beyond its initial spark. It also samples a part of the spectrum where dust re-radiation becomes important, which matters in a region wrapped in obscuring grains. A simple ladder helps, and the visuals can make it intuitive. Near-infrared is the glow of very energetic electrons spiraling in magnetic fields, changing on minute timescales because the emitting region is compact. Mid-infrared is warmer and slower, often sampling a larger volume and a different balance of cooling processes, including synchrotron self-absorption and thermal emission from dust. X-rays are the sharp end of the spectrum, where only the most extreme particles can speak and where scattering processes can amplify small changes. On that ladder, 8 microns is not merely redder light, it is a different diagnostic of density, optical depth, and how quickly electrons lose energy. This is where James Webb's MIRI matters, because it changes what can be timed and what can be trusted. MIRI observes mid-infrared light where dust is less obstructive, and thermal backgrounds can be managed in space, rather than fought from the ground. It probes emission that can come from cooler electrons, warm dust, and broader regions of the flow, which makes it a bridge between fast flicker and slow heating. It also tests whether flare energy cascades outward into longer wavelengths as events evolve, instead of dying where it began. In practice, it turns a formerly blurry, heat-soaked band into a clean time series, one that can be compared to infrared and X-ray clocks. The instrument itself is part of the story, and the camera can linger on its design. MIRI is chilled to cryogenic temperatures so its own heat does not drown the signal. Mid-infrared astronomy is always fighting warmth, even from the telescope. Its detectors must measure small changes against a bright glowing universe, including the telescope structure and the zodiacal light that fills the solar system. Even the mirror and sunshield have to behave like quiet machinery, because tiny drifts can masquerade as variability in a crowded field. In space, with stable pointing and careful calibration, those faint variations become measurable, and time-domain astronomy becomes possible at wavelengths that once felt inaccessible. Mid-infrared is not just a different colour, it is a different physical question. If a flare is a localized reconnection spark, it may brighten briefly and cool quickly, leaving little behind beyond a short-lived infrared spike. If a flare signals a state change, it may heat a larger volume and persist across bands, because the plasma conditions have shifted more globally. If energy is building towards something bigger, mid-infrared should reveal a widening footprint, more area, more mass involved, and more sustained emission. That footprint would be visible not only in brightness, but in the flare's shape, its duration, and whether it arrives with delays that imply expansion. That footprint can be described in plain terms, even when the physics is subtle. A small flare is like a match struck in a gust, bright for a moment and then gone, because the fuel is limited and the heat escapes. A larger change is like the coals underneath catching, spreading heat through the whole bed of fuel and changing how the fire behaves. Mid-infrared gives us a way to tell which picture fits, because it is sensitive to what happens after the first flash. If the glow lingers, it hints that energy is being stored in a bigger volume, rather than radiated immediately. The chapter's hinge is an event that arrives quietly, then refuses to be ignored. In early 2025, JWST detects a flare at roughly 8.1 microns with Miri, emerging from the crowded heart of the Milky Way. It is described as the first mid-infrared flare detection from Sagittarius A in this regime, and that phrasing carries weight beyond celebration. First ever matters here because it is not just chronology, it is capability. An entire band of behaviour becomes observable. It also matters because earlier attempts were limited by Earth's own heat, which turns mid-infrared observing into a battle against the planet. The visuals at the galactic centre are always deceptive, and the narration can slow down to show why. Along the line of sight, tens of thousands of stars pile into a single field, and dust lanes cut across them like smoke, hiding and revealing different layers. The black hole itself is invisible, yet its position is marked by the tight orbits of nearby stars, which swing around an unseen point with clockwork precision. Those stellar orbits were the evidence that turned Sagittarius A from a radio curiosity into a measured supermassive black hole. In that glare and clutter, a mid-infrared flare is a needle that moves, and it must be separated from everything else that also glows. Miri's sensitivity makes faint, fast variability measurable in a crowded, dusty field, and that is not a trivial achievement. Its wavelength penetrates dust that still complicates shorter bands, reducing confusion from extinction, changes that can mimic brightness variations. Its stability enables time domain monitoring that does not smear brief events into averages, which is essential when the physics changes on orbital timescales. At the galactic centre, an orbit near the innermost stable region can be measured in minutes, so timing is not a luxury, it is the whole experiment. The detection is a proof that mid-infrared flares are real, not merely predicted by models that had no direct test. That proof carries historical weight, because Sagittarius A has been watched for decades in other bands. Radio observations mapped the compact source long before anyone could time flares at minutes and seconds, and they established that something dense and energetic lived at the centre. Near-infrared monitoring later revealed the now familiar pattern of frequent outbursts and rapid substructure, which looked like turbulence made visible. X-ray observatories added their own view, catching occasional high-energy flares that were rarer but more dramatic. Mid-infrared had remained a gap, partly because Earth's atmosphere and thermal glow make it punishing from the ground, and partly because crowded fields demand exquisite resolution. In older mid-infrared images, the background itself shimmered, and the uncertainty could swallow the signal you wanted. So a mid-infrared flare is not just another data point, it is a new lever. It lets astronomers test whether the same electrons that shine at 2 microns survive long enough to radiate at 8 microns, or whether the population must be replenished. It probes whether the emitting region expands, cools, or changes optical depth as the flare evolves, which is how you distinguish a compact spark from a spreading disturbance. It also helps separate synchrotron emission from other contributions that can masquerade as variability, including warm dust and blended stellar backgrounds. In other words, it tells you whether you are seeing the flare itself or the environment responding to it. The documentary can show this as a sequence of light, sliding down the spectrum. A near-infrared spike rises and falls like a heartbeat on a monitor, sharp enough to feel immediate and alive. Then, slightly later or slightly broader, a mid-infrared bump appears, softer, warmer, and more persistent, as though the event has left an afterglow. The question becomes whether that bump is a fading echo, or the signature of a larger disturbance that is recruiting more material. If the bump spreads in time, it suggests expansion, because a growing region tends to smear sharp peaks into wider ones. A mid-infrared flare also invites a specific kind of dread, because it can be read two ways. It can be the cooling tail of a near-infrared event, sliding to longer wavelengths as electrons lose energy and the spectrum reddens. Or it can be evidence that a larger region is heating, involving more mass and more stored energy, which is how small variability sometimes becomes big variability. If the second reading is true, the next step is often X-rays, because hotter electrons and scattering processes tend to follow. The audience may not know the equations, but it can feel the logic of escalation. To make that fork in interpretation concrete, the narration can describe the electrons themselves. In a synchrotron flare, electrons are accelerated to relativistic speeds and radiate as they spiral in magnetic fields, converting kinetic energy into light. As they lose energy through radiation and expansion, their emission shifts to longer wavelengths, and the flare reddens over time in a predictable way. That predictability is powerful because it ties color changes to cooling times, which depend on magnetic field strength and particle energy. If the flare instead reflects a broader heating episode, the whole particle distribution can change, and the spectrum can harden rather than soften, which is a more ominous signature. X-rays are the genre where black holes start to look dangerous, at least on paper. In many active galactic nuclei, strong flares coincide with high-energy X-ray emission, and sometimes with changes in spectral slope that imply a hotter electron population. X-rays often trace a hot corona above the disk, where electrons are energetic and densities can be high enough for repeated scattering. They can also arise when infrared or optical photons are boosted upward by inverse Compton scattering, which turns a modest flare into a high-energy announcement. In that sense, X-rays are a stress test, because they demand extreme particles or extreme efficiency. The corona is worth picturing, because it is both real and mysterious. It is not a solid object, but a region of very hot, tenuous plasma threaded by magnetic fields, hovering above the denser flow-like weather above an ocean. In luminous systems, it can act like a furnace above the disk, converting gravitational energy into high-energy photons with surprising efficiency. Its temperature can reach tens to hundreds of billions of degrees in electron terms, although the plasma is so thin that temperature means average energy rather than a glowing surface. When the corona brightens, it often signals that the accretion flow is reorganizing, because geometry and magnetization control how energy is partitioned. Inverse Compton is simple in concept and ominous in implication. A lower energy photon collides with a relativistic electron and leaves with more energy, as if it has been kicked upward into a harsher band. If enough energetic electrons are present, infrared photons can be upscattered into the X-ray band, and the X-ray light curve begins to track the infrared. The effectiveness depends on density and electron energy, so it is a diagnostic of how many fast particles exist and how long photons stay trapped. When that happens during a flare, it suggests a hotter, more powerful particle population, and it hints that the system is approaching a different operating mode. There is a visual way to show this without turning it into a lecture. A soft photon enters a cloud of fast electrons, and after a scattering it exits as a hard photon, shorter in wavelength and sharper in energy. The process repeats, and the spectrum grows a high-energy tail, as though the event has found a way to climb the ladder. In astrophysics, that tail is often the telltale signature of a corona that has become efficient, rather than merely present. The audience can watch the ladder being climbed, rung by rung, and understand why the top rung matters. So the suspense builds around a clean prediction that viewers can understand. If Sagittarius A is ramping toward a more active state, the mid-infrared flare should have an X-ray companion, because the same energy release should populate the highest energy electrons. If the accretion flow is changing regime, the high-energy channel should light up with correlated variability, not just isolated flicker. If the engine is truly awakening, it should announce itself in the hardest photons, the ones that are hardest to produce by accident. The story is not asking for a catastrophe, only for a signature that the rules have shifted. The documentary can heighten the moment by showing synchronized clocks, because timing is the language of causality. One panel tracks the mid-infrared light curve, rising above the baseline like a tide that should pull other bands with it. Another panel shows the X-ray counts, waiting for a spike that would feel like a warning siren, sharp and unmistakable. The audience learns to expect a match, because in many energetic systems the bands move together, and the delay between them can reveal the mechanism. Even a lag of minutes can separate direct synchrotron X-rays from upscattered X-rays, and that distinction changes the story. The crucial result lands as an absence, and the absence is the relief. Simultaneous observations show no X-ray counterpart to the 8.1 micron flare, even as the mid-infrared brightening becomes clear and statistically robust. The mid-infrared event happens, yet the high-energy sky stays quiet, as though the flare never found the pathway upward. The expected signature of a major accretion state change does not appear, and the narrative has to pivot from escalation to constraint. In a genre built on explosions, it is the silence that carries the plot. That quiet X-ray channel is not boring, it is decisive, because it rules out whole classes of explanations. It means the flare did not produce a large population of ultra-energetic electrons, at least not in the numbers required for detectable X-ray emission at the galactic center distance. It means inverse Compton scattering did not suddenly become efficient, which would have pushed photons into the hard band even if the initial flare began in infrared. It means the corona, if present, did not flare in sympathy, and the system did not behave like a scaled-down active nucleus. The result narrows the parameter space, which is how science turns drama into understanding. In observational terms, this is where timing matters as much as sensitivity, and where simultaneity becomes a scientific weapon. If the X-rays had spiked minutes later, it could have implied delayed upscattering or a separate heating episode propagating through the flow. If they had risen slowly, it could have suggested a broader change in the accretion geometry, perhaps a temporary increase in density or magnetization. Instead, the simultaneity turns the absence into a constraint, and the constraint reshapes the narrative toward a smaller, faster process. It is a reminder that not every brightening is a climb, and not every flare is a step toward a new state. That missing X-ray signal is not a null result, it is a constraint with teeth. It implies the flare did not produce a large population of ultra-energetic electrons, and it limits the energy density of any hot corona during the event. It suggests the plasma stayed in a relatively modest temperature range, at least for the electrons that radiate efficiently and can be detected. It argues against a transition toward a quasar-like mode, because quasar-like behavior is defined by sustained high-energy output, not by isolated mid-infrared spikes. The absence also hints that the emitting region may be optically thick enough at some frequencies to trap photons, yet still too thin to generate strong Compton amplification. The implication is subtle but powerful, because quasars are not just brighter versions of Sagittarius A, so quasar-like luminosities require sustained accretion, efficient radiation, and often a disk structure that can feed a persistent corona, rather than a tenuous, turbulent flow. They also require the system to keep energy in radiating particles rather than hiding it in ions, winds, or swallowed heat. A single mid-infrared flare without X-rays is the opposite of that trend, and it points to a different kind of engine. It is a reminder that brightness is not only about mass, but about how matter couples to fields and how long it stays near the radiating zone. The interpretation that fits is smaller, sharper, and more local, and it matches what low luminosity accretion theory has long suggested. The event looks like a confined magnetic reconnection flare inside a low luminosity accretion flow, where turbulence twists field lines into stressed configurations. Magnetic energy is released in a compact region, accelerating electrons enough to brighten infrared bands, and then the system relaxes. The process stays thermodynamically limited, so it does not run away into a hotter state that would light up X-rays. In that picture, the mid-infrared flare is not a warning. It is a measurement of how reconnection behaves under extreme gravity. Magnetic reconnection deserves a moment of attention because it is the engine behind many cosmic flashes, and it scales across environments. In a plasma, magnetic field lines can break and reconnect, converting stored magnetic tension into heat and particle acceleration with startling efficiency. On the Sun, reconnection drives solar flares and coronal mass ejections, and the physics is familiar enough to be measured in detail. Near a black hole, the same process plays out in stronger gravity and faster orbital shear, where the timescales compress and the energies per particle can rise. The difference is that the plasma is collisionless and relativistic, so the microphysics of how particles get accelerated becomes part of the mystery. The film can show this as invisible geometry made visible. Field lines loop and braid in a turbulent flow, then snap into a new configuration, releasing energy in a burst that brightens a compact knot of plasma. That knot shines, then fades as the particles cool, expand, and escape into the surrounding flow, leaving only a brief signature in the light curve. The flare is dramatic, but it is not a regime change, and the missing X-rays are the clue that keeps it contained. Even the shape of the flare matters, because a fast rise and slower decay is the fingerprint of impulsive heating followed by cooling. Thermodynamically limited sounds abstract, so the narration grounds it in budgets and bottlenecks that govern every flare. The inner flow has a finite supply of fuel and a finite store of magnetic stress at any moment, because the inflow is thin and the density is low. Cooling processes drain energy as radiation, expansion and particle losses, preventing indefinite buildup even when turbulence keeps stirring the plasma. Without sustained inflow, the system cannot keep heating itself into a new regime, and it cannot maintain the conditions that produce persistent high-energy emission. In plain language, the engine can spark, but it cannot keep the spark fed. The budget can be framed as a balance sheet the audience can picture, and it clarifies why flicker does not imply escalation. Gravity provides the potential energy, but only some of it becomes light, and only some of that light reaches us through dust and confusion. In a radiatively inefficient flow, much of the energy stays locked in hot ions, which radiate poorly compared to electrons and can carry heat inward. Some energy is carried away by outflows, and some is swallowed across the horizon without a final flash, which is a quiet ending that still counts. The result is a system where variability is easy, but sustained brilliance is hard. In practical terms, Sagittarius A is restless because it is underfed, not because it is gearing up. The accretion rate is low, so the flow is hot and turbulent, yet radiatively inefficient, and that inefficiency is the key to its personality. Much energy stays in ions or escapes in outflows instead of becoming bright light, which keeps the overall luminosity modest. The engine sputters and sparks, but it lacks the continuous fuel that powers quasars, and the missing X-rays underline that limitation. If anything, the flare shows how efficiently the system can dispose of energy without letting it accumulate. That underfed state has been part of the Galactic Center story for a long time, and it is written into the environment itself. The Milky Way contains plenty of gas overall, yet the central parsec is a harsh place, with strong tides, intense radiation fields, and frequent shocks. Gas that drifts inward can be heated, stirred, and expelled before it settles into a bright thin disk, and angular momentum can keep material from plunging straight in. Even stellar winds from massive stars can both feed and disrupt the flow, delivering material while also injecting turbulence. The result is a black hole that is active, but in a constrained, low-efficiency way, and its flares are the visible punctuation. This is the calming twist that reframes the chapter's tension without killing the mystery. The monster is not asleep because Webb already showed constant flicker and frequent flares in the near-infrared, and that variability is real activity. The monster is also not awakening into apocalypse because the energy does not climb into X-rays here, even when mid-infrared finally lights up. It behaves like embers that flare in gusts, not an inferno that spreads, and the distinction is the scientific result. The audience is left with a different kind of suspense. If not escalation, then what pattern are we actually seeing? The metaphor works because it captures both motion and limitation, and it fits what the data are actually saying. Embers can flare suddenly when oxygen reaches them, and the brightness can be startling in the dark, especially when you are watching closely. Yet the flare is bounded by the amount of fuel and the shape of the coals, and it fades when the gust passes and the heat diffuses. Sagittarius A looks like that, alive with small releases but not building toward a blaze, at least not in this episode. The mid-infrared detection adds realism to the metaphor, because it shows the warmth after the flash, not just the flash itself. The sleeping giant metaphor needs a correction that keeps the drama honest and makes the science sharper. Sagittarius A is not a dormant beast waiting for a single trigger, because it is already variable on short timescales and already threaded by magnetic turbulence. It is a low-feeding engine with persistent reconnection, intermittent particle acceleration, and rapid cooling that prevents accumulation. It is active in a constrained way, like a campfire that crackles without catching the forest, and the missing X-rays are the proof that the flame stayed low. The real question becomes not whether it will wake, but what rules govern its restlessness. That distinction matters for the central question, because it separates threat from clue, and it changes what the audience should listen for next. JWST reveals a black hole that is variable across bands, yet still fundamentally low luminosity in its overall power output, which is why the Milky Way remains a quiet galaxy. The discoveries do not signal a galaxy-threatening phase change in the present, and the missing X-rays reinforce that with a hard constraint. They signal a laboratory where plasma physics plays out near a horizon, and where each band adds a new diagnostic. One flare becomes a calibration point for models, and the silence becomes part of the measurement. A laboratory is not a downgrade, it is a gift, because the conditions are extreme yet observable in real time. The gravitational field sets rapid orbital times, so changes happen on human-friendly timescales of minutes and hours, not centuries. The magnetic fields and particle energies push known physics into a regime we cannot reproduce on Earth, yet the signals arrive as light curves we can time and compare. Each flare becomes an experiment run by nature, with Webb acting as the sensor and with X-ray silence acting as the control. The audience can be invited to wonder how many physical processes announce themselves only by what they fail to do. The chapter also addresses why headlines keep sounding like physics is breaking, even when the underlying story is more disciplined. Part of the answer is that variability feels like agency when it is not explained, and the mind turns randomness into intention, especially in a place called a black hole. Part of the answer is that first-ever detections invite exaggerated narratives, because novelty is easily mistaken for danger, and because the word flare carries emotional weight. But the deeper answer is that the galactic center is crowded with structures that look anomalous, even when the black hole is behaving normally, and the eye is easily fooled. When you cannot see through dust directly, every new wavelength feels like a revelation, and revelations invite myth. The visuals can reinforce that crowding, because the region is almost unfair to the eye. Filaments of dust cross the frame, glowing in infrared like smoke lit from within, and their edges look sharp enough to suggest invisible forces. Star clusters pack the scene with points of light, and gas streams arc in complex curves that overlap in projection, turning depth into confusion. In mid-infrared, the dust has a textured sheen, as though the galaxy has been dusted with warm ash that catches every stray photon. Against that backdrop, any new flare or feature can feel like a sign, even when it is a normal consequence of turbulence and orbital shear. If Sagittarius A arm is not the true anomaly, then the camera has to pan outward, and the narration can let the audience feel that shift. The immediate vicinity is dramatic, yet it may be the most modelable part of the scene, because the physics is compact and the timescales are short enough to constrain. Nearby, the environment holds morphological riddles that do not sit neatly inside flare models, and they persist even when the black hole is quiet. The strangest shapes may belong to the ecosystem, not the horizon, and that is where the mystery migrates. The flare becomes a solved clue, while the surrounding architecture remains an open question. This widening of the frame does not abandon the black hole, it contextualizes it, and it preserves the chain of cause and effect. A low-luminosity nucleus still interacts with its surroundings through gravity, winds, and intermittent energy release, even if it never becomes a quasar. Gas clouds feel tides, shocks, and shear as they orbit, and dust responds to heating, collisions, and radiation pressure from nearby stars. The neighborhood is where long-term history is written, even when the central engine stays modest, and the structures remember what the flares forget. In that sense, the missing X-rays are not just reassurance, they are a boundary condition for everything around the whole. This is where the documentary widens the frame without losing the thread of cause and effect, and it uses the mid-infrared result as a pivot. The black hole's flares are local diagnostics of magnetic reconnection and cooling, and the missing X-rays sharpen that diagnosis into something specific. The surrounding region is a test of how feedback, tides, and turbulence sculpt gas and dust over time, leaving patterns that can outlast any single flare. The question shifts from what the whole is doing to what the neighborhood is becoming, and whether the environment is the real storyteller. If the center is a weather system, then the flare is lightning and the clouds are the plot. The transition is a pivot from energy to architecture, from light curves to structures. We move from the black hole's immediate emission zone to the surrounding galactic center ecosystem, where dust and gas draw strange geometries that look engineered. We ask why star formation should be suppressed there, yet strange structures keep appearing, as though the region is both hostile and creative. The next chapter follows those structures as the real riddle comes into focus, and it asks what forces are shaping them. As the camera pulls back, the center of the Milky Way becomes less like a point and more like a weather system. Streams, knots, and cavities overlap in projection, and the infrared reveals layers that visible light cannot penetrate, like fog illuminated by headlights. The black hole remains the anchor, but it is no longer the only character, and the silence in X-rays still echoes as a constraint. In the shadows around it, the shapes themselves begin to ask questions, and the film prepares to listen. The transition is a pivot from energy to architecture, from light curves to structures. We pull away from the horizon's flicker and ask what the neighborhood is becoming, because in the galactic center, even neighborhood is deceptive. Distance compresses and forces overlap until the scene feels engineered. Less like scenery, more like a machine under load. Sagittarius A sits at the Milky Way's dynamical center, but it is not alone. Around it lies the central molecular zone, a dense, turbulent reservoir of gas and dust, where the galaxy's ordinary rules are rewritten. The CMZ is both fuel and battlefield, because gravity pulls inward while feedback pushes outward, and neither side ever fully wins. That tug-of-war is not abstract. It leaves scars in temperature, velocity dispersion, and magnetic geometry, which telescopes can read like bruises. Geographically, the CMZ spans the inner few hundred parsecs of the galaxy. That is only a small fraction of the Milky Way's diameter, yet it holds an outsized share of its molecular material, concentrated where pressures are higher than in the disk. In practice, it is a crowded warehouse where cold clouds, warm plasma, and dust lanes are stacked in the same volume, sometimes occupying the same line of sight. Gas streams orbit in elongated paths, collide, shock, and shear under the central potential, and those encounters inject turbulence that can persist for millions of years. From a distance, the central region looks like a bright seam stitched into the Milky Way's midline. As we zoom in, that seam breaks into lanes, arcs, and knots, structures shaped by gravity, but also by pressure gradients and magnetism that can redirect flows. Dust does not merely obscure the view. It marks where gas has cooled, condensed, and survived long enough to become molecular, building complex chemistry on grain surfaces. Even the darkness has texture here, because extinction varies across clumps and filaments, and the background starlight is carved into mottled silhouettes. Those orbits are not simple circles, and that matters for everything we see. In the inner galaxy, the gravitational field is steep and lopsided, shaped by the bulge and the bar, so gas responds to a potential that is both deep and asymmetric. Gas can be driven onto families of elongated trajectories, and the streams can intersect at predictable traffic points, where crowding becomes unavoidable. When they do, kinetic energy turns into heat, turbulence, and compression, ingredients that can either trigger collapse or prevent it, depending on how fast the energy dissipates. The bar's influence is subtle in pictures, but brutal in dynamics. It can torque gas, draining angular momentum and nudging material inward in fits and starts, rather than as a smooth inward spiral. Instead of a steady flow, the CMZ behaves like a set of conveyor belts that occasionally jam, storing energy as pressure and motion. When a jam releases, the resulting collision can light up chemistry and shock tracers across tens of light years, briefly making invisible impacts visible. In spiral arms, cold clouds drift in gentler rotation and form stars along coherent lanes. In those calmer districts, the gas can cool efficiently through familiar molecular lines, and gravity can gather it into cores with time to settle into equilibrium. In the CMZ, the same raw material is stirred harder, heated more often, and compressed unpredictably, so the gas rarely enjoys a long quiet interval. The result is a region that should be a star factory, yet behaves like a throttled engine, revving high while producing surprisingly little output. The contrast is visible even before the science is explained. In wide-field infrared maps, the disk looks like a structured braid of dust lanes, and the center looks like a knot pulled tight. The CMZ glows with warm dust emission, and it flickers with line radiation from molecules excited by shocks, as if the gas is constantly being struck and relit. It is a place where the interstellar medium rarely gets to rest, because energy keeps arriving from orbits, stars, and collisions. If we could stand inside it, the CMZ would not feel like empty space. It would feel like weather, eddies of gas, pressure fronts, and invisible fields that push back when you try to move, even though the density is still far below any earthly vacuum chamber. The temperature ranges are extreme, from cold molecular pockets to hot ionized cavities that can reach thousands of degrees, with sharp boundaries between phases. Even where the gas is cold, it is often warmer than similar clouds in the disk, and that extra heat changes how easily gravity can take control. This chapter shifts the mystery about the terrifying anomaly to Sagittarius C. Escar C lies roughly 300 light-years in projection from Escar, embedded within the CMZ, close enough to share the same harsh rules. Yet it is distinct enough to expose them, because local conditions can amplify one mechanism while muting another. If the centre is a storm, Escar C is a particular wall of cloud where the lightning keeps striking, leaving patterns that refuse to look orderly. Sagittarius C is also a reminder that the galactic centre is not one landmark. It is a landscape of named complexes, each with its own balance of ionized gas, molecular reservoirs, and embedded stars, and each acting like a different experiment run under the same gravity. Astronomers mapped these regions long before they could see them in sharp infrared detail, because dust blocks visible light almost completely. They did it by listening to radio waves that slip through dust like sound through fog, tracing ionized gas and molecules by their spectral fingerprints. Historically, Sagittarius C has been a familiar name in radio astronomy. Long before Webb, radio maps traced bright emission from ionized gas and revealed non-thermal filaments in the central region, suggesting populations of relativistic electrons moving through magnetic structures. Those earlier observations hinted that magnetism is not a minor detail near the centre, and that energetic particles are part of the environment. They also suggested that Escar C sits at an intersection of phases, cold molecular reservoirs beside hot ionized cavities, with boundaries that can shift over time. That history matters because radio astronomy built the first reliable geography of the inner galaxy. In the mid to late 20th century, surveys of hydrogen recombination lines and molecular transitions sketched the CMZ as a dense ring-like zone, even when the true three-dimensional shape remained uncertain. Later, polarization measurements revealed ordered magnetic components on large scales. Even as smaller scales stayed chaotic under turbulence. JWST kept appearing as a complicated boundary, where different regimes touch and exchange energy, and where simple models tend to break. James Webb's infrared view reveals a striking structure near Escar C. A roughly 25 light-year region of ionized hydrogen glows where ultraviolet photons have stripped electrons from atoms, creating an H2 region that shines through recombination and fine structure emission. In Webb's palette, that glow is not a uniform fog, but a textured sheet with ripples and seams like illuminated smoke stretched thin. Threaded through that glow are thin, needle-like filaments that cut across the field, some bright enough to look etched into the scene. The camera does not simply show brightness, it shows contrast in physical conditions. Ionized hydrogen emits in characteristic lines when electrons recombine and cascade through energy levels, releasing photons at specific wavelengths that act like thermometers and density probes. Dust grains, warmed by nearby stars, radiate a smoother infrared continuum that fills the background like embers, revealing where energy is being absorbed and re-radiated. Against that ember glow, the needles stand out, sharp, bright, and strangely deliberate, as if someone scored the nebula with a blade. The scene has a particular kind of tension, like a fabric pulled too tightly. Bright knots punctuate the ionized region, and faint wisps connect them like stretched threads, implying that the gas is not smoothly distributed but broken into fragments. Some needles look razor straight, while others bend slightly, as if pushed by invisible currents or caught in shear. Against the darker background, their edges appear crisp, an indication that the structures are narrow compared to the field of view, and that the transitions in density or ionization are abrupt. As the view glides across the field, the eye keeps catching sudden linear flashes. A filament appears, then another, then a cluster that looks almost like shattered glass suspended in a glowing haze, with gaps that feel too clean to be accidental. The brightest strands seem to trace boundaries, as if they are outlining cavities or shock fronts, where compression makes emission spike. Yet the boundaries do not close into neat bubbles, and that refusal is part of the unease, because it suggests forces that do not expand symmetrically. The needles do not line up like combed hair. Their orientations look chaotic, intersecting and diverging without a single dominant direction, and the pattern resists the comforting logic of a single sculptor. Some run nearly parallel for a short distance, and then abruptly cross others at sharp angles, forming junctions that look like stress points. In many star-forming regions, filaments and pillars show coherent shaping by radiation and magnetic fields, and you can often infer the dominant direction. Here, coherence is the very thing that seems missing, and the absence becomes the clue. That missing coherence is not just a visual quirk, because the CMZ is expected to impose order. Large-scale shear tends to stretch structures along orbital directions, and large-scale magnetic fields can align dust and plasma, leaving preferred orientations even in messy environments. In many environments, those influences leave a statistical fingerprint, even when turbulence adds noise and local feedback complicates the picture. SGRC looks like the fingerprint has been smudged on purpose, as if multiple hands pressed down at different times. In typical H2 regions, massive stars carve cavities and drive ionization fronts. Ultraviolet photons create expanding bubbles of ionized gas, and the boundary between ionized and neutral material becomes a moving front, compressing gas as it advances. Pillars point back toward the radiation source, and filaments often trace ordered magnetic geometry, especially where dust grains align with the field. The morphology reads like a wind tunnel experiment, where forces leave a clear signature, and the geometry tells you where to look for the engine. That signature is more than aesthetic because it encodes directionality. If a cluster of O-type stars dominates, you can often draw a line from a pillar's head to the source, and the brightness gradients confirm the direction of irradiation. If a large-scale magnetic field is strong, dust polarization and filament orientation can align with it, revealing a preferred axis across the region. In many nearby nebulae, the geometry is a map of cause and effect, and the map is legible. SGRC reads differently, like a magnetic maze. The ionized gas appears shredded into narrow strands, with angles that resist a simple explanation, and the region feels less like one bubble than a field of competing boundaries. If magnetic fields are guiding the plasma, they are not acting like one clean, large-scale field, and that is the unsettling implication. The scene suggests competing domains, as if the region is stitched from patches with different magnetic histories, each patch remembering a different disturbance. That scrambled appearance is the anomaly, and it is easy to misplace it. The terrifying part is not a single object hiding near the black hole, waiting to be discovered like a monster in the dark. The terrifying part is an ecosystem where fields, shocks and tides compete, and the evidence is written in geometry that refuses to simplify. The needles are like forensic marks, thin, bright and stubbornly ambiguous, pointing to processes that overlap rather than line up. To understand why this matters, we need the basic physics of filaments. Ionized gas is a plasma, meaning its particles respond collectively to electromagnetic forces, so the gas can behave like a fluid tied to invisible lines. In a plasma, charged particles spiral around magnetic field lines, and that spiraling makes cross-field motion difficult, especially when collisions are infrequent. Ionized gas follows magnetic field lines more easily than it crosses them, so fields can act like guides, fences, or scaffolding. This is the same principle that shapes auroras on Earth, scaled up to interstellar distances. Electrons and ions gyrate around field lines with a characteristic radius that shrinks as the field strengthens, and that radius sets how tightly the plasma is magnetized. When the gyroradius is small compared to the structure, the field acts like rails, and the plasma streams along them. Sideways diffusion becomes slow and inefficient, so narrow features can persist longer than intuition suggests. The strength of that guiding effect depends on the balance of pressures. Thermal pressure tries to smooth the gas, ram pressure from flows tries to pile it up, and magnetic pressure resists bending, acting like an extra stiffness in the medium. There is also magnetic tension, which acts like an elastic restoring force along curved field lines, pulling them straighter when they are distorted. When the magnetic energy density rivals the kinetic energy density, the field becomes a structural beam rather than a tracer, and morphology becomes magnetic engineering. In practical terms, the field can decide whether a compression becomes a clump or a sheet. A shock that would normally collapse into a dense knot can instead spread along field lines, producing a filament, especially when cooling is efficient and the post-shock layer thins. Conversely, a tangled field can trap energy, sustaining turbulence that keeps gas stirred, and that stirring can keep density peaks from surviving. The same magnetic influence can therefore both create fine structure and prevent the final step into gravitational collapse, which is why the maze matters. If one ordered field dominated CZ, many filaments would share a preferred direction. Even if the gas were turbulent, the average alignment would still reveal itself statistically, like grain in wood showing through scratches. Instead, Webb shows needles that look misaligned, as if multiple field domains overlap and compete within the same projected area. That suggests turbulence, local drivers, or repeated disturbances that reorient the field, and it also suggests that the region may be layered along the line of sight. Layering is a quiet complication in the galactic center. Along our sight line, multiple clouds at different distances can overlap in projection, even if they are separated by tens of light years and moving at very different speeds. A filament that appears to intersect another may be in front of it, or behind it, or moving at a different velocity entirely, and the image alone cannot untangle that depth. The maze could be partly real, and partly a trick of depth, which is exactly why interpretation becomes tense. The CMZ supplies many ways to scramble order. Clouds collide at higher relative speeds than in the disk, so shocks are stronger and more frequent, and the resulting turbulence is harder to dissipate. Shocks propagate through dense gas, and shear stretches structures along orbital paths, sometimes turning clumps into streams before they can settle. Radiation fields are stronger, and cosmic rays may be more abundant, adding ionization and heating deep inside clouds. Each of those ingredients can modify ionization, chemistry, and pressure on short timescales, so the medium is constantly being rewritten. Even the chemistry tells a story of violence. In shocked gas, molecules can be dissociated and then reformed, and dust grains can be sputtered, releasing elements into the gas phase and changing which coolants are available. Those changes alter cooling rates, which then alter how easily gas can compress and how long dense pockets can survive. In the CMZ, the interstellar medium is not merely moving, it is constantly being processed, as if the galaxy is running it through a grinder. Processing has consequences for what the gas can become. Cooling depends on specific molecules and fine structure lines, and those depend on density, temperature, and composition, which shocks and radiation can reset. When shocks and radiation repeatedly disturb the chemistry, the gas can spend less time in the calm conditions where gravity quietly wins, and more time in transitional states. The CMZ is therefore not just dense, it is dynamically and chemically restless, and restlessness is the enemy of slow collapse. SGRC sits where these influences can stack rather than cancel. It is near molecular material that can feed new stars, and near ionized regions that mark recent feedback, so it contains both fuel and evidence of disruption. It is also near the gravitational gradient that amplifies tidal stresses, because the potential steepens toward the center. The closer you are to the center, the more the galaxy behaves like a differential machine, pulling harder on one side of a cloud than the other, and that differential pull changes what stable means. That differential pull is not a metaphor, it is a measurable tidal field. A cloud that would be stable in the disk can be stretched and heated as it orbits the center, and its internal structure can be unzipped by shear. If its self-gravity is not strong enough, it can be shredded into streams before it fragments into stars, leaving long filaments of molecular gas that never become clusters. The CMZ therefore tests clouds the way a fast river tests a raft, exposing weaknesses quickly. Star formation theory expects a relationship between gas density and star formation rate. In its simplest form, more dense gas should yield more stars, given enough time because gravity has more material to work with. Observationally, this idea is often summarized through empirical scaling relations that work well in galaxy disks, where conditions vary but remain within a familiar range. The CMZ violates that expectation, showing abundant dense gas with surprisingly low star formation efficiency, as if something is holding the brake down. That violation is not subtle, and it has forced a recheck of assumptions. Are we measuring the right dense gas, or is it dense in a way that does not translate into collapsing cores, perhaps because it is warm, turbulent, or magnetically supported? Are the timescales different, so the CMZ is caught in a temporary phase of accumulation, storing gas before a burst? Or is the environment injecting energy so persistently that the usual conversion rules no longer apply, turning density into a misleading proxy? This is the paradox that frames JWST. The environment contains the ingredients for starbirth, yet the recipe fails more often than it succeeds, and the failure is itself a physical state. The filaments are not just pretty structures, they are clues to why the gas stays unproductive, because they trace where energy is being guided and dissipated. They hint that energy is being injected faster than gravity can organize matter, into collapsing cores, and that the injection may be directional, intermittent, and layered. Several inhibitors operate simultaneously near the galactic center. Turbulence raises internal velocities, supporting clouds against collapse by adding non-thermal pressure that mimics extra heat. Shear stretches clouds and disrupts coherent contraction, especially along elongated orbits where neighboring streams move at different speeds. Tidal forces can tear marginal clumps apart before gravity wins, and the threshold for survival becomes higher. Each effect is familiar, but their combination is unusually intense here, and the combination is the story. Turbulence in particular is a double-edged tool. In one context, turbulent compression can create dense pockets that collapse, briefly giving gravity a head start. In another, turbulence acts like a constant shaking that prevents long-lived density peaks, erasing them before they can deepen. In the CMZ, the driving may be continuous, fed by orbital energy, cloud collisions, and feedback, so the gas never fully relaxes into a quiet, fragile state. The needles may be the visible edges of that agitation, where plasma is forced into narrow channels. A useful way to think about it is to compare timescales. Gravity needs time to amplify a small overdensity into a collapsing core, while turbulence can erase that overdensity in a crossing time, and shear can stretch it before it condenses. If the turbulent crossing time stays short, collapse becomes a rare event that requires unusually strong compression, not just ordinary density. The CMZ may therefore form stars only when turbulence briefly loses control, like a storm eye opening for a moment. Magnetic pressure adds another layer of resistance. Strong fields can provide support, slow fragmentation, and change how shocks compress gas, because the field resists being squeezed in certain directions. Even when gas is dense, it may be magnetically stiff, requiring higher pressures to collapse, and those pressures may be hard to sustain. In plain language, the cloud can be heavy, yet still braced by an invisible framework, and that framework can redirect collapse into sheets and strands. The bracing also changes how angular momentum is redistributed inside clouds. If the gas is well coupled to the field, collapsing material can drag field lines and build magnetic tension, storing energy like a twisted rubber band. That tension can act like a brake, slowing rotation and altering fragmentation into multiple cores, which changes cluster formation. The outcome is not simply fewer stars, but a different pattern of star formation, with different masses and different timing. Radiation also changes the balance. Intense ultraviolet fields ionize surfaces, drive photoevaporation, and heat gas that would otherwise cool, pushing it toward higher sound speeds. Heating increases sound speed and raises the gene's mass, shifting what kinds of stars can form and how much mass must gather before collapse begins. That shift matters because forming massive stars requires assembling large masses quickly, before feedback disrupts the reservoir, and the CMZ makes that race even tighter. Cosmic rays and X-rays can add a quieter kind of heating. They penetrate deeper than ultraviolet light, ionizing gas inside clouds and altering magnetic coupling, which changes how easily neutrals can slip past field lines. Increased ionization can make the gas better, tied to magnetic fields, which can slow the drift that gravity needs to concentrate mass. In the CMZ, even the dark interiors may not be as insulated as they are in the disk, so the word shielded becomes relative. So why do we see ionized needles at all? The filaments imply sculpting processes that act on plasma, not just cold molecular gas, and they imply confinement in a region that should be chaotic. Their thinness suggests strong guiding or compression, and their brightness suggests ongoing excitation or recent energization, because ionized gas cools and recombines unless it is continually powered. The question becomes which processes can carve long, thin structures in a region this hostile, and whether one process can dominate. The answer may not be singular, because the environment is not singular, and SQRC may be a crossroads. One hypothesis is colliding stellar winds. Massive stars in the CMZ drive fast winds that crash into surrounding gas, carrying momentum and magnetic fields outward, and those winds can reach thousands of kilometers per second. Where winds collide with dense material, they produce shock fronts that heat and compress the plasma, and the post-shock gas can glow in infrared lines. Wind collisions can create thin shells and instabilities that fragment into strands, especially when magnetic fields guide the flow and cooling makes the layers thin. In that picture, each filament is a boundary where ram pressure and magnetic tension balance. A wind pushes outward, the surrounding medium pushes back, and the magnetic field resists being bent too sharply, concentrating stress into narrow regions. Shocks compress ionized gas into narrow ridges, then turbulence breaks them into segments, leaving a field of bright slivers. Different wind sources can impose different directions, producing a tangled map that looks like disagreement frozen into light. The instability physics is important here, because thin layers rarely remain smooth. When a shock-compressed sheet accelerates into surrounding material, it can develop ripples that grow into fingers, and those fingers can become filaments if the field channels them. Cooling can make the layer thinner, which makes it more prone to fragmentation, because small perturbations matter more in a thin sheet. If the magnetic field is locally strong, it can guide those fragments into elongated strands rather than clumps, preserving the needle-like look. A second hypothesis is plasma jets from massive protostars. Even in harsh environments, some protostars launch collimated outflows along their rotation axes, and those jets can remain narrow over long distances when magnetic fields help collimate them. Those jets can be partly ionized, and they can drive bow shocks into their surroundings, compressing and heating gas along their paths. If those jets propagate into ionized gas, they can punch channels and create filamentary wakes, which glow where shocks excite emission lines. Protostellar jets would naturally create narrow linear features. They could also vary in orientation, because each forming star has its own disk axis, and the CMZ does not provide a single alignment. If many young objects contribute, the result could look like a field of needles without a common direction, and the chaos would be real rather than projected. The key question becomes whether there are enough young sources nearby to explain the density of filaments, and whether their velocities match what jets would require. A third hypothesis is intense ultraviolet radiation shaping ionization fronts. UV photons can erode dense clumps, leaving behind elongated structures as the surrounding gas is stripped away, and the remaining cores cast shadows that shape the flow. In calmer regions, those structures point toward the ionizing stars and form coherent pillars, with heads that remain neutral longer. The tails are ablated into ionized flows, and the geometry often reads like arrows. Near SGRC, the UV field may be complex and multi-source, arriving from different clusters and reflecting off uneven dust distributions. If ionizing radiation arrives from several directions, pillars lose a single pointing vector, and the carved edges can look contradictory. Photoionization can then carve edges and strands that look disordered in projection, especially when clumps move rapidly through the radiation field. In addition, if the gas is moving quickly, the ionization front can be distorted, producing curved and intersecting features that mimic a maze. A fourth hypothesis involves shocks from cloud-cloud collisions and expanding bubbles. In the CMZ, orbiting streams can collide and generate strong shocks, and feedback can inflate cavities that sweep up shells, compressing gas into thin layers. Shocks can compress gas into thin sheets, and instabilities can roll those layers into filaments, especially when the post-shock region cools and collapses in thickness. When multiple shocks overlap, the geometry can become tangled quickly, and the resulting filaments can point in many directions. Shocks also interact with magnetic fields in a way that can amplify complexity. Compression strengthens the field component parallel to the shock front, which can make the post-shock region more anisotropic, favouring filament formation over clump formation. Subsequent turbulence can fold and twist the field, leaving filaments that trace a history of impacts rather than a single present-day driver. In that sense, each needle could be a fossil of a past collision, preserved because the field kept it narrow. None of these hypotheses excludes the others. The CMZ is not a single-process laboratory, it is a superposition of drivers, and CRC may sit where several drivers overlap. Winds can collide inside a region already shaped by radiation, and jets can propagate through gas, already shocked by cloud impacts, reusing old channels. The needles may be the integrated record of winds, jets, radiation, and shocks acting over different times, and that integration is what makes the image feel like a puzzle box. That is why the anomaly feels terrifying to interpret. A single image can contain multiple epochs of activity layered along the line of sight, and the center is crowded in depth as well as in the sky. What looks like one chaotic structure may be several structures, each shaped by a different event, and projection can turn separation into apparent collision. The question becomes unsettlingly simple. How many histories are we seeing at once, and which one is driving the present? Webb's advantage is sensitivity and resolution through dust. Its infrared instruments can see emission lines from ionized gas while also tracing warm dust and embedded stars, revealing both the energized surfaces and the hidden sources. It can separate ionized emission from surrounding continuum and reveal fine structure that earlier telescopes blurred into haze. Yet even Webb cannot instantly separate cause from coincidence without additional traces, because morphology alone can lie. The geometry is a clue, but it is not a verdict, and the maze demands more than one kind of evidence. To turn geometry into physics, we need to add motion. A filament created by a jet should carry a different velocity signature than a filament created by a swept-up shell, and that difference can be measured as Doppler shifts in spectral lines. A shock front should show broadened line widths, while a photoionized edge might show a cleaner gradient, tracing expansion or evaporation. The maze is therefore also a code, and spectroscopy is the key that can start reading it, translating brightness into dynamics. This is where the narrative returns to the central question. What did JWST actually reveal about the galactic center, and does it signal threat or clue, monster or mechanism? SGRC suggests the deeper clue, because the puzzle is environmental rather than apocalyptic, and the evidence points to regulation rather than catastrophe. The danger is not that something is coming, but that our assumptions may be wrong, and wrong assumptions spread quietly through every model we build. The phrase stars shouldn't survive needs careful handling. It does not mean star formation is forbidden near the center, or that gravity somehow stops working in the CMZ. It means the thresholds and efficiencies differ, and the usual disk-based rules mispredict outcomes, because the environment changes the accounting. In other words, the same density does not guarantee the same outcome when turbulence, tides and fields change the balance sheet. Stars do form in the CMZ, but the process is biased and intermittent. Collapse may require rarer, higher pressure events such as strong shocks or converging flows that can overcome turbulence and magnetic support at least briefly. When those events occur, they can assemble massive clumps quickly, but the window may be short before feedback disrupts the reservoir. The result can be bursts of formation separated by long periods of suppression, so the center breathes in episodes rather than in steady rhythm. That episodic behavior has a practical implication for what we observe today. A region can look gas-rich and star-poor simply because it is between bursts, still gathering material and still being stirred, and the calm is only apparent. Then, when conditions tip, it can light up quickly and violently, producing massive clusters and intense feedback that reshapes the neighborhood. The CMZ may therefore be less a steady factory and more a pressure cooker, with release valves that open unpredictably. SGRC becomes a case study in that revised regime. The ionized region indicates recent or ongoing massive star influence, because only hot stars supply enough ultraviolet photons to keep hydrogen ionized over tens of light years. The surrounding molecular material indicates remaining fuel that has not yet converted efficiently into stars, despite being dense enough to tempt the usual scaling laws. That juxtaposition, feedback beside unused gas, captures the CMZ paradox in one frame. It invites a question that is almost uncomfortable. What is stopping the rest from following, and what would it take to change the answer? If the needles trace magnetic structure, they imply that fields are dynamically important, not just decorative. If they trace shocks, they imply that compression is episodic and violent, and that the gas is being restructured faster than it can settle. If they trace jets, they imply that protostars are forming despite the hostility, and that local pockets can still win brief victories. Each interpretation changes how we model star formation in extreme environments, and each one changes what we should search for next, because the diagnostics differ. In spiral arms, we often assume turbulence decays and clouds settle into collapse, following a relatively orderly sequence. We imagine a cloud cooling, fragmenting, and forming clusters in a chain of steps that mostly proceed forward. In the CMZ, turbulence may be continuously driven by orbital dynamics and feedback, so the gas can remain young in a dynamical sense, always being reset before gravity completes its work. The needles may be the visible edges of those resets, places where the medium reveals its constant reprocessing. That difference matters beyond the Milky Way. Many galaxies host central molecular zones, and some undergo starbursts where the center lights up with rapid star formation, briefly dominating the galaxy's output. If we misread the CMZ physics, we misread how starbursts ignite and how they shut down, and we misinterpret the timing of those events. We also misread how gas feeds central black holes, because the same transport processes can deliver fuel inward, and the same turbulence can delay it. There is a historical echo here, because galactic centers have long been treated as special cases. Early models often emphasized the black hole as the main actor, and everything else as scenery, because the black hole was the most dramatic object we could name. Over time, observations forced a broader view, where the interstellar medium becomes a co-equal player, shaping what the black hole can eat and when. SGRC is part of that shift, an argument written in filaments, insisting that the environment is not passive. That shift is also methodological. As instruments improved, the center stopped being a blur and became a laboratory of competing mechanisms where each wavelength reveals a different phase of the same system. Each new band added a missing layer, from radio maps of ionized gas to infrared maps of dust to millimeter maps of cold molecules and dense cores. Webb's image is therefore not an isolated revelation, but a sharp new slice through a long-standing mystery, adding fine structure where we once had only glow. The cosmology tie-in is not optional. It is the reason Webb's view matters at all scales. In the early universe, galactic centers were more common and more extreme, because gas fractions were higher and galaxies were assembling rapidly. Mergers were frequent, central turbulence was stronger, and inflows were more violent, so dense gas lived under constant disturbance. Under those conditions, the distinction between normal disk and extreme center blurs, and the early universe may have looked more like the CMZ than like our quiet spiral arms. JWST is now observing high redshift galaxies during rapid growth. Their light often comes from compact, dusty regions that resemble scaled-up CMZ conditions, even if we cannot resolve them into individual clouds, and even if the physics is compressed into a single pixel. Understanding SGRC helps interpret those distant systems without relying on oversimplified local analogies, because it teaches us what dense gas can look like when it is not efficiently forming stars. It gives us a physical vocabulary: turbulence, shear, magnetic support, rather than a purely photometric guess. If star formation can be suppressed even with abundant dense gas, then high redshift luminosities need careful decoding. Brightness may reflect short bursts rather than steady conversion, and dust can hide the true distribution of young stars, making a galaxy seem quieter than it is. Feedback and turbulence may regulate growth more strongly than naive gas-to-star scaling, and the regulation may be intermittent rather than continuous. The question becomes not only how much gas, but what state is the gas in, and how quickly can that state change? SGRC also reframes what we mean by the terrifying anomaly. The anomaly is not a singular threat near SGR A lurking like a secret, and it is not a single filament that breaks the rules. It is the possibility that our mental map of the galactic center is too centralized, too focused on the black hole alone, and too confident in disk-based intuition. The center is not a point, it is a system, and systems can behave in ways that are harder to predict because they remember their past. The black hole is still the anchor, because it shapes the gravitational potential and the orbital shear, setting the stage for everything else. Yet the visible complexity may be driven by the broader engine of the CMZ, where gas flows, stalls, collides, and reroutes, and where feedback keeps rewriting boundaries. The monster is not one mouth, it is a whole circulatory system, and the filaments may be the capillaries where energy is exchanged. If that sounds dramatic, it is also literal, because energy and momentum really do circulate through these structures. That system has supply lines, choke points, and turbulent reservoirs. Gas must move inward through a maze of orbits, shocks, and magnetic stresses, and along the way, angular momentum must be redistributed, because inward motion requires losing rotational support. If the filaments are signatures of that motion, then we should follow the gas, not just the light, and ask where the flow accelerates or stalls. The maze is not only magnetic, it is dynamical, and dynamics is what connects SGRC back to SGR. This is the narrative escalation that keeps momentum in a middle chapter. The viewer is led to ask what feeds this chaos, and how it connects back to the black hole, because the maze must have an upstream source. The answer cannot come from Webb alone, because we need kinematics and cold gas tracers, not just illuminated surfaces. We need to know not only what glows, but what moves, what collides, and what is about to collapse, before the next burst rewrites the scene. We need to see the flows that deliver material into the CMZ and redistribute it within. We need to identify where shocks occur and how angular momentum is transported. because those are the mechanisms that decide whether gas accumulates or disperses. We need to know whether the needles mark outflow, inflow, or stalled circulation, and whether they are boundaries or channels. And we need to ask one more question. How long can a region remain in this suspended state before it flips into a burst? And what would that flip look like in velocity? That is where ALMA enters the story. ALMA maps cold molecular gas and measures velocities through spectral lines, turning frequency shifts into motion, and turning motion into a three-dimensional hypothesis. It can reveal rotating structures, shear-driven streams, and vortices that look like space tornadoes, where gas curls under competing forces. Where Webb gives us the illuminated surfaces, ALMA gives us the mass and the momentum, the hidden bulk that actually carries the story forward. It is the difference between seeing smoke and seeing the wind. If Webb shows the ionized skin, ALMA shows the cold skeleton underneath. Together they can link filaments to the larger gas dynamics that sustain them, and they can test whether the maze is one structure or many layered ones. The terrifying anomaly becomes a solvable question about transport, not a supernatural warning, because transport leaves measurable signatures in velocity fields. The maze becomes navigable if we can trace the currents that built it and the stresses that keep it sharp. Follow the gas. If filaments are signatures, then the supply lines must exist. Enter ALMA's space tornadoes. Follow the gas. If filaments are signatures, then the supply lines must exist. Enter ALMA's view of the central molecular zone, where the Milky Way's core is fed. In visible light, the galactic center is a wall, but in radio it becomes a moving diagram. The camera doesn't just pan across scenery here, it listens for physics. ALMA works in millimeter and submillimeter radio, where cold molecular gas actually speaks. These wavelengths are long enough to slip through much of the dust that blocks starlight, so the central dust lanes fade from opaque to translucent. The emission is not a smooth glow, but a barcode of spectral lines. Each line comes from a specific molecule, and each molecule survives under specific conditions. That is why radio astronomy can be both a map and a laboratory. In the CMZ, the key emitters include carbon monoxide, hydrogen cyanide, fermion ion, and carbon monosulfide. CO is abundant and easy to excite, so it traces widespread molecular material, including gas that is relatively diffuse. HCN and HCO+ require higher densities to glow strongly, so they highlight compact clumps and compressed lanes. CS and other sulfur-bearing species often brighten where densities rise and chemistry is stirred. Even before motion is measured, the mix of lines already hints at pressure, density, and irradiation. ALMA's strength is not only sensitivity but resolution, an interferometric trick that synthesizes a telescope kilometers wide. Dozens of antennas spread across the Atacama Desert act like a single instrument, and their combined signals reconstruct fine structure. In practice, that means filaments that would blur into a smear become threads with edges. It also means the same region can be observed in multiple molecular transitions, each one sampling a different temperature or density layer. The CMZ becomes a stack of physical slices, not a single flat image. Dust that blinds visible light becomes nearly transparent, and molecules radiate in narrow spectral lines. Those lines come from CO, HCN, HCO+, CS, and other traces that survive in dense, cold clouds. The phrase cold is relative, because the CMZ is often warmer than typical disk clouds. Temperatures of tens to over 100 Kelvin are common, which is still cold by human standards, yet hot enough to reshape chemistry. In the galactic center, those clouds carry most of the mass that could become stars or fuel. Radio maps are not only pictures of where gas sits, they are maps of how gas moves, because every spectral line is a clock and a speedometer. The key is Doppler shift. Motion toward us pushes a line to higher frequency, motion away shifts it lower. This is the same effect that changes a siren's pitch, but here it is measured with exquisite precision. ALMA resolves frequency so finely that a small shift becomes a measurable velocity. With enough pixels, those velocities become a flowing field. By measuring the shift across the sky, ALMA builds a velocity field, not just a brightness map. The result is often stored as a spectral cube, where two axes are sky position and the third is velocity. When that cube is sliced, filaments can appear and vanish depending on which velocity channel you choose. Some structures that look connected in a static image separate into distinct streams when velocity is revealed. Others, which seem unrelated on the sky, align into a single coherent lane in position, velocity space. Motion becomes the organizing principle. Line width adds another layer because broad lines often mean turbulence, shocks, or overlapping streams. Thermal motion broadens lines a little, but in the CMZ, the dominant broadening is usually non-thermal. Supersonic turbulence, shear, and unresolved substructure can widen profiles far beyond what temperature alone allows. Broad wings can indicate accelerated gas, as if a shock has kicked material into a faster tail. Split peaks can mean two streams crossing the same line of sight. Every profile is a clue, but it must be read with caution. This is the missing dimension behind Webb's filaments. JWST shows ionized skins and warm dust, which are the surfaces that light up. Those skins are real, but they are also selective, because they highlight where radiation and shocks touch the gas. ALMA shows the cold bulk underneath, where momentum and angular momentum decide what happens next. That bulk is where most of the mass lives, and mass is what gravity negotiates with. When the two are combined, the question becomes mechanical rather than mystical. Where is the gas being compressed? Where is it being shredded? And where is it being redirected? In the combined view, a bright infrared filament can be a boundary layer, not the main body. The warm dust can mark where grains are heated, while the cold gas behind it carries the inertia. Ionized emission can trace an interface, while molecular lines trace what is being pushed. The center stops looking like a static photograph and starts behaving like a fluid simulation. The mystery shifts from what is it to what is it doing. In ALMA's kinematic view, the CMZ is not a calm ring of fuel. It is a circulation system with lanes, merges, and sudden collisions. Gas follows elongated orbits shaped by the bar and the central potential, then crowds at predictable junctions. Those orbits are not perfect circles because the Milky Way's bar distorts the gravitational field. In barred galaxies, gas tends to stream along dust lanes and transition between orbit families. The CMZ is where those streams pile up and argue with each other. At those junctions, streams intersect at high relative speed, and kinetic energy turns into heat and turbulence. The conversion is not gentle because gas is collisional and cannot pass through itself like stars can. When streams meet, shocks form, and shocks dissipate energy into internal motion. The CMZ behaves like traffic under gravity. Flow is continuous, but smoothness is rare. Even when the overall circulation persists, the local conditions can change abruptly. A cloud can be calm on one side and shredded on the other. Inside that traffic, ALMA reveals ephemeral, violent streams that observers nickname space tornadoes. The term is a metaphor for motion, not a claim about air or weather. There is no atmosphere here, only molecular gas in near vacuum, responding to gravity, pressure, and magnetic fields. The physics is rotation, shear, and strong velocity gradients across narrow structures. The tornado label points to twisting flows that look like vortices in position, velocity space. A space tornado is not a single object with a stable eye. It is a transient pattern created when shocks and shear force gas into spiraling, braided, or rolling motion. In maps, it can appear as a rotating filament, a curved streamer, or a compact swirl where velocities flip sign across a small region. In spectra, it can appear as split components, steep gradients, and unusually broad line wings. The key idea is that the CMZ is constantly generating these patterns, then destroying them. Think of a river confluence where currents collide, but replace water with gas 1 billion times thinner. The flow can curl back on itself, forming eddies that live for a while and then dissolve. In the CMZ, those eddies are shaped by gravity and by the bar's shear, so their geometry can look stretched and angular. If magnetic fields thread the gas, they can guide the motion, tightening or resisting the twist. The tornado is therefore a signature of competing forces. It is a visible argument between inertia, pressure, and tension. The visuals here are deceptive in a productive way. A filament that looks like a single rope may actually be multiple strands at different velocities, layered along our line of sight. A compact swirl may be a projection of two streams crossing, not a bound rotating core. ALMA helps separate these cases by showing how velocity changes across the structure. Even then, the interpretation must remain disciplined, because the galactic center is crowded. The data are rich, but the geometry is unforgiving. Shocks are the main sculptors that create these shock highways. In the CMZ, shocks come from several sources that overlap in time. Supernova remnants drive expanding fronts that slam into nearby clouds, compressing and shredding them. Massive stars inflate wind bubbles that collide with dense gas, creating thin, compressed shells and turbulent wakes. Cloud-cloud collisions occur because orbit families intersect, and because streams crowd near pericenter. Orbital crowding itself becomes a shock engine, because gas cannot pass through itself without dissipating energy. Supernova shocks carry a particular kind of violence, because they begin as supersonic blast waves. As the remnant expands, it sweeps up interstellar material, and the shock slows while still remaining disruptive. When that front hits a dense molecular cloud, the shock can wrap around clumps, driving instabilities at the interface. The cloud's outer layers can be ablated and mixed into the flow, while denser cores survive longer. The result is a ragged boundary, bright in shock traces and turbulent in kinematics. Stellar winds add a steadier sculpting pressure. Massive stars dump momentum into their surroundings for millions of years, carving cavities and pushing shells outward. Where those shells encounter dense gas, they can compress it into arcs and ridges. The shell can fragment, because thin layers are unstable when pushed and cooled. In radio maps, these regions can look like curved lanes with coherent velocity patterns. In infrared, they can glow as heated dust and ionized rims. Cloud-cloud collisions are less cinematic in origin, but they are brutally efficient at stirring gas. In the CMZ, relative velocities can be tens of kilometers per second, which is enough to generate strong shocks. When two clouds collide, the interface can become a dense, turbulent slab. That slab may briefly resemble an ideal star-forming site, because density rises quickly. Yet the same collision injects kinetic energy that must dissipate before gravity can take over. The collision is both a trigger and a delay. Orbital crowding is the quiet architect behind many of these events. As gas streams along elongated paths, it slows near turning points and compresses where trajectories converge. That compression can be predictable in a statistical sense, even if individual clouds behave chaotically. The bar's gravitational torque can also drive gas inward by removing angular momentum. But the inward drive is not smooth, because the gas responds by shocking and fragmenting. The highway exists, but it is under constant construction. Each shock does three things that matter for the story. It compresses gas, raising density, and briefly making collapse easier. It triggers chemistry, because sputtering and heating release molecules and change line ratios, marking the shock in specific traces. It injects turbulence, because the post-shock flow becomes unstable and breaks into eddies and shear layers. Compression and turbulence arrive together, and that duality is the CMZ's signature. Compression is straightforward in principle, but subtle in consequence. A shock increases density and pressure, and it can also increase temperature depending on how quickly the gas cools. In molecular gas, cooling can be efficient through line emission, but the CMZ's environment complicates that cooling. Cosmic rays, intense radiation fields, and repeated shocks can keep the baseline temperature elevated, so the gas may become denser without becoming truly cold. Gravity prefers cold density, not just density. Shock chemistry is one of ALMA's most revealing gifts. Dust grains in calm clouds lock away elements, coating themselves with icy mantles and trapping silicon in mineral cores. A shock can sputter those grains, knocking molecules and atoms back into the gas phase. That sudden release changes what lines become bright, like a dye injected into a flow. It also changes the ionization balance, which affects how gas couples to magnetic fields. Chemistry is not decoration here, it is a tracer of energy transfer. Turbulence is the third gift, and it is the most double-edged. Turbulent motion provides support against gravity, acting like an extra pressure term in the equations of collapse. It also creates density fluctuations, which can seed clumps that later become cores. In the CMZ, turbulence is often so strong that it dominates the energy budget of clouds. That can keep clouds from forming stars efficiently, even when they are dense by disk standards. The center becomes a place where gas is heavy, yet restless. This is where the star formation paradox becomes less mysterious. The CMZ contains dense gas that should form stars efficiently, yet it often does not. Shocks can raise density, but they also raise temperature and velocity dispersion. Turbulence acts like extra pressure, increasing the effective Jeans mass and delaying gravitational collapse. Magnetic fields can add stiffness, making compression anisotropic and preventing fragments from becoming bound cores. The same processes that create dense structures can keep them from settling into stars. The gene's mass is a simple idea with dramatic implications. If gas is warmer or more turbulent, the minimum mass that can collapse increases. That means small clumps that would become stars in the disk may remain unbound in the CMZ. Instead of fragmenting into many low-mass cores, the gas can stay in fewer, larger structures. Those structures may orbit, collide, and shear apart before collapse completes. The paradox is not that gravity fails, but that gravity is forced to compete. Magnetic fields complicate the competition in a way that is easy to visualize. Field lines behave like stretched rubber bands embedded in the gas, resisting motion across them and guiding motion along them. When shocks compress gas, they can also compress and amplify magnetic fields. That increases magnetic pressure and tension, which can prevent isotropic collapse. The gas may flatten into sheets or stretch into filaments rather than condensing into compact spheres. The CMZ's geometry can therefore be a magnetic fingerprint. Space tornadoes therefore have a split personality. They can funnel gas inward by draining angular momentum and by guiding flows along compressed lanes. They can also starve the center by keeping gas stirred, heated, and unbound so it never becomes a steady reservoir. They can create short-lived clumps that look like fuel, then disperse them before they reach the inner parsec. The feeding is real, but it is clumpy, intermittent, and inefficient. Angular momentum is the quiet gatekeeper in this story. Gas cannot simply fall inward because it carries rotational motion inherited from the galaxy's larger rotation. To move closer to the center, it must shed that angular momentum through torques and dissipation. Shocks are one of the few efficient ways to do that, because they convert ordered motion into heat and turbulence. Magnetic stresses can also transport angular momentum, especially when ionized fractions are sufficient for coupling. The result is a slow leak inward, punctuated by sudden drops. ALMA's velocity maps make that intermittency measurable. Some streamers show coherent inflow signatures, with velocities consistent with gas losing angular momentum. Other features show counterflows and shear, where adjacent lanes move in opposite directions. Some regions show line broadening that implies strong turbulence rather than ordered inflow. The CMZ is not a pipeline, it is a mixing layer with occasional delivery events. It behaves more like a braided river than a single channel. In a braided river, channels split and rejoin, and sandbars appear and vanish. The CMZ has an analogous behavior, except the sandbars are dense clumps, and the water is molecular gas. A lane can look like a direct path inward, then dissolve into a fan of fragments. A collision can create a bright knot, then shear can stretch it into a filament. ALMA captures these states as snapshots, and the viewer must imagine the motion between them. The story is written in gradients. Connect this back to Sagittarius A and its filamentary maze. Webb's needles can sit on boundaries where shocks compress ionized gas, while ALMA traces the cold molecular lanes that created the boundary. A filament can be the lit edge of a shock front, while the mass rides behind it in cold gas. If multiple shocks overlap, the maze becomes a palimpsest of boundaries, each tied to a different stream. The geometry looks chaotic because the kinematics are chaotic. In that maze, the eye is tempted to see intention, as if the filaments were drawn. The physics offers a different explanation, and it is more unsettling because it is impersonal. Boundaries form where pressure jumps, where ionization fronts meet dense gas, and where shear layers tear. The bright lines are often the thinnest parts of the structure, like foam on a wave. Behind them, the cold gas carries most of the momentum. The visible pattern is an outline of deeper motion. Now connect it back to Sagittarius A and the bubbling disk. JWST saw persistent flickering and frequent flares, with no strict periodicity. That behavior fits a black hole fed by a chaotic supply chain rather than a steady disk. If the inflow arrives as clumps and filaments, the inner flow's density and magnetization fluctuate. Those fluctuations change how often magnetic reconnection occurs and how much energy each event releases. The flicker becomes a symptom of variable delivery, not a countdown. Near the black hole, the gas is no longer molecular, and it is no longer cool. It becomes a hot plasma, where electrons and ions swirl in magnetic fields and radiate in infrared and radio. In such a plasma, magnetic reconnection can rapidly convert magnetic energy into particle energy. That energization can brighten the emission for minutes, then fade as particles cool or escape. If the feeding is irregular, the magnetic configuration is constantly being reset. The light curve becomes a seismograph of supply. A turbulent supply also explains why Escorial stays dim overall. The CMZ contains gas, but most of it does not reach the horizon. Angular momentum, shocks, and feedback keep recycling material in the inner few hundred light years. When gas does move inward, it can be heated into a radiatively inefficient flow that swallows energy rather than radiating it. The black hole is underfed, and underfeeding naturally produces variability without sustained brightness. Radiatively inefficient accretion is a technical phrase with a plain meaning. The gas is so hot and tenuous that it cannot easily radiate away its energy before falling inward or being blown outward. Instead of shining like a bright quasar disk, the flow stores energy in ions and magnetic fields. Some of that energy can power outflows, which further reduce the mass that reaches the horizon. The center becomes a leaky system, where much of the inflow is recycled. Dimness is not absence, it is inefficiency. The documentary needs a clear cascade from large scales to small scales. The CMZ spans roughly 300 light years in radius, and its shocks evolve over thousands to millions of years. Yet JWST sees variability on minutes, which corresponds to regions only a few gravitational radii across. The bridge is a chain of instabilities and transport steps, not a single direct pipe. Large-scale collisions create clumps and turbulence. Turbulence seeds intermittent inflow, and intermittent inflow modulates the inner plasma. That cascade is one of the most important conceptual visuals in the chapter. On the larger scales, gravity and the bar shape the flow, setting the lanes and junctions. On intermediate scales, shocks and turbulence break the flow into fragments and filaments. On smaller scales still, magnetic stresses and viscous-like processes move angular momentum outward. Finally, near the horizon, plasma physics takes over, and tiny changes can trigger bright events. The same gas changes character as it descends. Make the distances feel concrete without slowing the pace. A streamer can be tens of light years long, but it only needs to deliver a tiny fraction inward to change the inner flow. The inner accretion region is microscopic by comparison, yet it is sensitive to small changes in density. A modest clump arriving late can change magnetic field topology and trigger reconnection. The horizon scale flare is therefore the last link in a long mechanical chain. To ground that scale, imagine compressing the CMZ to the size of a city. The inner few gravitational radii would be smaller than a single room, yet the room's brightness could change the city's skyline at night. That is the asymmetry of black hole feeding, where the smallest region produces the most dramatic variability. It is also why remote sensing matters, because we cannot fly probes into this environment. We must infer the room's conditions from the city's traffic. Timescales also cascade, and that is part of the mystery's rhythm. A cloud collision can set conditions that persist for many orbits around the center. A shock-compressed lane can survive long enough to redirect gas into a new path. Yet the final plunge is governed by orbital times of minutes near the black hole. The viewer learns that the same system can be slow and fast at once, because different radii run on different clocks. Those clocks are set by gravity, and gravity is a strict timekeeper. Far from the center, orbital periods are long, and changes accumulate slowly. Closer in, orbital periods shorten dramatically, and the system can rearrange itself in a human viewing session. That is why JWST can watch the center flicker in real time, while ALMA maps structures that evolve over far longer. The narrative tension comes from connecting these clocks without pretending they match. The cascade is the connection. This is where the phrase shock highways earns its meaning. Shocks create compressed lanes that can guide gas like rails, briefly making transport more efficient. Those rails are unstable, because turbulence and shear keep tearing them apart. The result is a network that forms, breaks and reforms, constantly rerouting the flow. Feeding becomes episodic, and the black hole's light curve becomes the readout of that episodic network. A highway implies direction, but in the CMZ direction is negotiated. Some lanes may carry gas inward for a time, then a collision can deflect the stream outward or sideways. A shock can remove angular momentum, but it can also heat the gas and increase pressure, encouraging expansion. The same event can both deliver and disperse depending on geometry and timing. That is why the center can be rich in gas and still starved at the horizon. The fuel exists, but the delivery is unreliable. The physics behind the tornado metaphor must stay precise. Rotation can be real, but it is often shear-driven rather than a bound vortex. Velocity gradients can mimic spinning structures when multiple streams overlap along the line of sight. ALMA disentangles some of that by mapping velocities, but projection still complicates interpretation. The responsible claim is that the CMZ hosts strong vorticity and shear, not that it hosts stable atmospheric cyclones. Vorticity is simply a measure of a local rotation in a flow, and shear is a measure of how velocity changes across space. Both are common in the CMZ because the gravitational potential is steep and the orbits are elongated. When two lanes slide past each other, shear layers form, and those layers can roll up into Kelvin, Helmholtz-like structures. When a shock hits a clumpy medium, it can generate vortices behind obstacles, like wake turbulence behind a rock in a stream. These are familiar fluid behaviours, translated into an interstellar setting. The metaphor works because the mathematics is shared. Add the chemistry beat that makes shocks visible in radio. Shocked regions enhance certain molecules and excite higher transitions, changing line ratios across the map. Grain sputtering releases silicon and other elements, making Psi-O a classic shock tracer. Elevated temperatures populate higher energy levels, brightening lines that would be weak in calm clouds. ALMA can therefore tag shock locations, not only by motion but by molecular fingerprints. SiO is especially telling because silicon is usually locked inside dust grains. When a shock is strong enough, it liberates silicon into the gas, where it quickly forms SiO. That molecule then radiates in characteristic transitions that stand out against the background. Other tracers, like CH3OH, can also be enhanced when grain mantles are disturbed. The point is not memorizing molecules, but recognizing a principle. Chemistry remembers violence, even after the shock front has passed. Line ratios act like thermometers and densitometers, though they require careful modelling. A higher transition may require higher temperature or density to be excited, so its brightness relative to a lower transition encodes conditions. In the CMZ, those ratios can change sharply across a filament, implying a boundary between calm and shocked gas. When combined with velocity gradients, the case for a shock becomes stronger. The map becomes layered, with kinematics and chemistry reinforcing each other. This is how ALMA turns patterns into mechanisms, then connect chemistry back to star formation suppression. Shocks can keep gas warm, and warm gas resists collapse. Turbulence keeps line widths broad, which signals kinetic support against gravity. Magnetic fields can be amplified in compressed lanes, increasing magnetic pressure and tension. The combined effect is dense gas that is dynamically hot, which looks like fuel but behaves like stirred soup. In a calm disk cloud, dense gas can cool, settle, and fragment into prestellar cores. In the CMZ, repeated shocks can keep resetting that process before it completes. A clump begins to condense, then a new shock passes through, heating and stirring it again. Even without a direct shock, shear can stretch the clump, reducing its ability to become bound. The environment is not merely harsh, it is persistent. The gas is rarely allowed to rest. Now connect suppression back to feeding, because the paradox is the point. If gas does not collapse into stars, it remains available to move inward later. Star formation is a sink that locks gas into long-lived objects, while suppression keeps gas in circulation. The CMZ can therefore both inhibit starbirth and preserve a reservoir for future accretion events. The same turbulence that prevents stars can keep the black hole's pantry stocked, even if delivery is irregular. This reframes the CMZ as a regulator, not a failure. A center that converts gas into stars too efficiently may starve its black hole, at least temporarily. A center that suppresses star formation can retain gas, but only if it can transport angular momentum away. The CMZ sits in that uneasy middle ground, where gas accumulates yet struggles to settle. The question becomes not why no stars, but what balance is being maintained. The answer may be written in shocks. This is where stakes rise without invoking apocalypse. Understanding the CMZ is understanding why our black hole is quiet today, and why it was likely brighter in the past. Geological and gamma-ray evidence suggests the Milky Way had energetic episodes, like the Fermi bubbles, within the last few million years. Those episodes require changes in supply or feedback, not supernatural triggers. The CMZ's shock network is a plausible control knob for those changes. The Fermi bubbles, towering above and below the galactic plane, are like smoke stains on the sky. They imply that energy was injected from the centre on large scales, long after the dinosaurs had gone. The cause could be a burst of star formation, a period of stronger accretion onto SGRA, or a combination. Either way, the center must have been fed differently than it is now. That raises a quiet, unsettling question. What would it take for the supply chain to shift again? The CMZ is where that shift would begin. Broaden the context beyond the Milky Way, because this is not a local curiosity. Many galaxies host CMZ-like central reservoirs with dense, turbulent gas and suppressed star formation. In starbursts, the balance tips and centers ignite, converting gas rapidly into stars and sometimes feeding active nuclei. In quiescent spirals, the balance stays throttled, and black holes flicker rather than blaze. Our center is the nearest test case for models used across cosmic time. Historically, the idea of galactic nuclei as engines matured over decades. Early radio astronomy revealed bright cores in other galaxies, and quasars forced the conclusion that black holes could outshine entire galaxies. Later, surveys showed that many galaxies host dormant or weakly active black holes, suggesting duty cycles rather than permanent activity. The CMZ concept emerged as observers realized that gas supply, not just black hole mass, controls luminosity. Our Milky Way is a quiet nucleus, but it is not a simple one. Its quietness is an active state maintained by dynamics. That cosmic time link matters for JWST's broader mission. Webb observes early galaxies where gas fractions were higher and inflows were more violent. Those distant centers may resemble an extreme CMZ, but we cannot resolve their lanes directly. If we learn how shocks regulate feeding here, we can interpret unresolved light from high redshift more honestly. The Milky Way becomes a calibration target for black hole growth and feedback in the young universe. When Webb sees a distant galaxy brighten, we often infer accretion or star formation from integrated light. But integrated light can hide the same paradox we see nearby, where dense gas does not guarantee star formation. It can also hide intermittent feeding, where a nucleus flickers because supply arrives in clumps. The Milky Way offers a resolved laboratory for those interpretations. It lets us test whether turbulence and shocks can throttle growth without emptying the reservoir. That matters because cosmic history is written in growth curves. Insert the human exploration contrast because the audience expects a journey. Voyager and Voyager 2 crossed the solar system with hardware, and SpaceX sells the idea of physically going. This story is different. Our space documentary travels by remote sensing, built from photons that left the center 26,000 years ago. We do not fly into the CMZ, we reconstruct it from spectra, polarization, and timing. Yet the knowledge changes our map of the universe more than any rocket trajectory. There is a poetic inversion here that deserves to be spoken. The Voyagers carried gold records outward, but the galactic center sends its record to us continuously. Every spectral line is a message, and every Doppler shift is a verb. We are not passengers in this chapter, we are interpreters. The journey is made by calibration, by careful subtraction of noise, and by models that turn frequency into flow. That is slower than a rocket launch, but it reaches far deeper. That contrast also reinforces the theme of disciplined interpretation. Viral clips can claim we heard the black hole, or that a sound means danger. The reality is that ALMA measures frequencies, and astronomers translate shifts into velocities. JWST measures infrared brightness, and scientists translate variability into plasma processes. The drama is real, but it is encoded in data products, not in literal audio. The monster is revealed by calibration, not by fear. There is nothing wrong with sonification as a tool, because translating data into sound can reveal patterns. The problem comes when translation is presented as direct perception, as if the universe is screaming. In this chapter, the real sound is the spectral line's displacement, and the real music is turbulence written in line width. The center is not issuing warnings, it is obeying equations. The unease we feel comes from recognizing how energetic those equations can be. That is a more honest kind of suspense. Bring the narrative back to the central question with a tight synthesis. JWST's flickering is not an isolated anomaly at the horizon. ALMA's shock-driven tornadoes show why the supply is turbulent, clumpy, and intermittent. The CMZ is a chaotic circulatory system that can both feed and starve the core. The terrifying anomaly becomes a scientific one. The Milky Way's heart runs on unstable transport. So what are we really watching when the light curve jumps? We are watching the end of a supply chain that begins in a bar-driven flow hundreds of light-years out. We are watching shocks compress gas, turbulence shred it, and magnetic fields braid it into temporary lanes. We are watching angular momentum being negotiated, not eliminated. And we are watching a black hole respond to whatever arrives, however unevenly it comes. The flicker is not a message, it is a consequence. End with a transition that sets up the next chapter's confrontation with misinformation. The story has been visual, light curves, filaments, velocity maps, and shock tracers. But the internet heard sounds and turned translations into threats. Now we confront the viral claim head-on and separate sonification from signal. We leave Chapter 5 with a new map of causality. Large-scale shocks create temporary highways. Highways deliver clumps. Clumps drive turbulence near the horizon. The black hole flickers because its fuel arrives like weather, not like a pipeline. And the closer we look, the more the anomaly looks like physics doing exactly what it does in a turbulent universe. The question for the next chapter is simple, and it is urgent. How did careful data become a viral omen? The internet says James Webb heard a horrifying sound from Sagittarius A. The claim spreads fast because it feels like a warning, and because warnings are supposed to be heard. It also feels personal, because sound is how danger reaches us, through skin, through bone, through instinct. The clips arrive with familiar grammar, almost like a ritual the platform has taught us to recognize. A black thumbnail, a red circle, a timer that implies a countdown. The audio is metallic and rising, like a siren that has learned to sing. People share it with the same sentence. Listen to this. They do not say, look at the data, because the hook is not knowledge. The hook is the ancient reflex that says a rising tone means something is coming. But space is not an air-filled room, and the center of the galaxy is not a hallway where echoes travel. Sound is a pressure wave, and pressure waves need a medium that can compress and rebound. On Earth, that medium is usually air, but it can also be water, steel, or the ground beneath your feet. In interplanetary and interstellar space, the density is so low that acoustic waves cannot propagate like they do here. The vacuum is not perfectly empty, yet it is empty enough to break the everyday rules. Between stars there are particles, mostly hydrogen atoms and plasma, but they are spread so thin that collisions are rare. A useful comparison is almost cruel in its simplicity, because it collapses the myth in one number. At sea level, a cubic centimetre of air contains roughly 10 quintillion molecules. In much of interstellar space, that same volume might hold only a few atoms and sometimes less. A pressure wave cannot stay coherent when the stuff it needs is missing, because there is nothing to pass the push along. Even where plasma exists, it behaves differently than air, and it supports its own kinds of waves. Those are magnetohydrodynamic waves, guided by magnetic fields rather than ordinary compression. This is the vacuum reality check that the hype skips, because the check is quiet and the hype is loud. A black hole can shake plasma and bend spacetime, and it can drive shocks in surrounding gas. But it does not broadcast audible noise through empty space in the way a speaker broadcasts sound. If you stood near Sagittarius A, you would not hear a scream. You would see radiation, and you would feel tidal gravity long before any imagined soundtrack arrived. Even the word stood becomes absurd there, because the environment is lethal long before your ears could be disappointed. The confusion begins with a real concept that gets misused, and the misuse is subtle enough to sound scientific. Telescopes detect electromagnetic waves, not pressure waves. Light is an oscillation of electric and magnetic fields, and that oscillation can cross vacuum without needing matter. Infrared, radio, X-rays, and gamma rays travel through space because they do not require a medium. They are information carried by photons, and photons do not need air to move. That single fact is why astronomy exists at all, and why the universe can be read from across billions of light years. A detector does not record a soundtrack, even when the final product feels like one. It records photons, counts, energies, arrival times, and sometimes polarization. Astronomers turn those measurements into calibrated products like light curves and spectra, and those products are the real voice of the object. A light curve is not a melody, even if it rises and falls like one. It is brightness versus time, measured with careful corrections for instrument behavior and background glow. A spectrum is not a chord, it is brightness versus wavelength, shaped by physical processes like synchrotron emission, thermal radiation, and absorption. Those products can be translated into audio, but translation is not recording. Translation is interpretation, and interpretation requires choices. The person making the audio decides what becomes pitch, what becomes volume, and what becomes rhythm. That translation has a name, and it matters because naming is honesty. It is called sonification, and NASA uses it for education and accessibility. Sonification maps data features to sound features like pitch, volume, timbre, and rhythm, so patterns can be perceived in a different sensory channel. Brightness can become loudness, frequency can become pitch, and variability can become pulsing. A sharp spike in a light curve can become a sudden strike of a bell. A slow drift can become a glide of tone that feels like motion. Sonification is not a gimmick when it is labelled honestly, because it can reveal structure the eye misses. Human hearing is extremely sensitive to timing and repetition, especially when patterns are irregular. In time series data, a subtle quasi-period can become obvious when it becomes a beat. It can also help blind and low-vision audiences engage with astronomy, and that is not a side benefit. Accessibility is a scientific value because it broadens who can participate in discovery. When the mapping is transparent, sonification becomes another kind of graph, one you can listen to. The problem starts when a mapped sound is framed as literal audio captured at the source. The framing turns a teaching tool into a horror prop. It invites the audience to imagine a microphone floating beside an event horizon, faithfully recording a cosmic shriek. The viral clips often choose the most unsettling mapping because unsettling spreads. They emphasize dissonance, harsh tones, and rising intensity, and they compress the dynamics so the sound never relaxes. That aesthetic choice is not evidence of danger, and it is not a discovery. It is a reflection of irregular data being assigned to abrasive instruments and then edited for maximum dread. The same data could be mapped to soft chimes and gentle drones, and it would feel meditative. The physics would not change, only the emotional costume. Chaotic systems sonify into chaotic sound, and Sagittarius A is not a metronome. A light curve with jitter, spikes, and uneven spacing becomes a rhythm that feels anxious. A spectrum with multiple peaks becomes a chord that feels unstable, especially when the mapping favours close intervals. When the mapping uses minor keys and rough timbres, the brain hears threat even when the data only show variability. Our auditory system evolved to treat sudden changes as important. In the wild, a sudden change often meant something was moving toward you. Sagittarius A is variable, and Webb proved it with relentless clarity, minute after minute, flare after flare. The near-infrared flicker happens on seconds to minutes, which is astonishing for something 4 million times the mass of the Sun. Major flares appear several times per day without strict periodicity, and the irregularity is the point. That irregularity is a signature of turbulence and magnetic reconnection, not a coded message. The plasma near the black hole is hot, ionized, and threaded by magnetic fields. Those fields twist and tangle as gas spirals inward, and tension builds like stress in a stretched rope. Reconnection is what happens when that rope snaps and reties itself in a new pattern. Magnetic field lines rearrange, and stored magnetic energy is rapidly converted into particle energy and heat. Electrons are accelerated to near-light speeds, and those electrons radiate strongly in infrared and sometimes X-rays. So the so-called impossible sound is a category error, and the category error is doing most of the work. It confuses a vacuum with a medium, and a translation with a recording. It also confuses fear with information, and it treats a stylistic choice as a physical event. The real signal is not in the audio. The real signal is in timing, spectrum, and polarization, because those are the measurements that physics can answer. When we ask what happened, we ask when it brightened, how the colour changed, and how the light was oriented. This is the media literacy moment the story needs, because the galactic centre is too important to be reduced to a jump scare. Sensational thumbnails say terrifying, dangerous, and countdown, and they add red arrows like emergency signage. They do it because attention is scarce, and because fear is a reliable magnet. The tactics distort the science, but they also reveal something true about us. People are hungry for mystery, and the galactic centre supplies it in endless forms. We stare at the dark because we suspect it is not empty. We do not have to shame that hunger, because curiosity is the raw material of science. We can redirect it toward the real questions that are stranger than clickbait. The centre of the Milky Way is not a haunted house, yet it is still a place where the rules feel unfamiliar. It's a physical engine where gravity, plasma, and magnetism fight over energy, and the fight leaves traces. Gas clouds collide and shear, and magnetic fields channel motion into filaments. Stars are born in dense knots, and other stars die, seeding the region with turbulence. The documentary's promise is simple, and it is also a discipline. We replace the fake anomaly with the real anomaly, and we keep the dread as a tone while anchoring it in equations. We treat uncertainty as part of the discovery, not proof of conspiracy. The story has been visual, light curves and filaments, but the internet heard sounds. That mismatch is the hinge of this chapter, because it shows how easily data becomes myth. When you understand the hinge, you can open the door without falling through it. Once the sound myth is stripped away, a deeper tension appears, and it is not about audio at all. Sagittarius A is the nearest supermassive black hole, and it sits inside a messy galactic ecosystem. Webb sees its infrared flares, while ALMA sees shock highways and rotating flows in the central molecular zone. Together they turn the center into a laboratory for fundamental physics, because we can watch cause and effect across scales. The horizon scale plasma responds on minutes, the surrounding molecular gas responds on thousands of years, and the galaxy responds on millions. The same engine runs through all of it. There is also historical weight here, because Sagittarius A was not always an obvious black hole. For decades it was a bright radio source at the galaxy's center, compact and strange. The name Sagittarius A itself carries that history, an asterisk added to mark the most intriguing component. That history includes a slow sharpening of vision, from radio interferometers to adaptive optics that could pierce the dust. The galactic center is hidden behind thick lanes of interstellar grains, which scatter visible light and turn the core into a silhouette. Infrared astronomy changed the game, because longer wavelengths slip through where optical light is blocked. The case became decisive through patient measurement, not dramatic sound. Astronomers tracked stars orbiting an invisible focus, and the orbits tightened the noose around alternative explanations. By the early 2000s, the mass and compactness implied a supermassive black hole, with little room for doubt. That same tradition of careful measurement is now pushing into new territory, and the first paradigm pressure point is gravity itself. Dark matter explains galaxy rotation curves and large-scale structure, and it fits a vast range of observations. Yet some modified gravity and emergent gravity ideas attempt to reproduce those effects without particle dark matter. Many of these ideas predict that in strong gravity environments, the usual dark matter-like behavior could weaken or change, because the effective law depends on acceleration scale. In plain terms, they claim the extra gravity we attribute to dark matter might not act the same near a massive compact object. If that is true, the galactic center becomes a critical arena. Sagittarius A is a stress test for those claims, because the gravitational field near the black hole is extreme and sharply varying. If gravity behaves differently than general relativity predicts, the deviations should show up in precise measurements. The question is not philosophical, and it is not about vibes. It is measurable, and the measurements already exist in outline. We measure stellar orbits, especially the tight, fast stars like S2, whose period is about 16 years. We measure precession, orbital plane changes, and relativistic redshift, and we compare them to the predictions of general relativity. When S2 swings through pericenter, it reaches thousands of kilometers per second, and its light shifts in a way that encodes gravity. That shift is not a metaphor. It is a change in wavelength caused by motion and by the depth of the gravitational potential. We also measure how mass is distributed in the central parsec, and whether any extended component is required beyond the central point mass. A distributed cluster of dark objects could, in principle, mimic some effects, but it would have signatures in orbital evolution. Over time, those signatures become constraints. We measure gravitational lensing and dynamical effects on gas, even though the region is crowded and dusty. Lensing near the center is subtle, because the angles are small and the background is complex. Yet in principle, it constrains how spacetime is curved, and it provides another check on mass distribution. Gas dynamics in the inner region respond to the potential, though turbulence complicates interpretation. The gas is not a clean test particle, because magnetic fields and pressure forces matter. Still, the overall flow patterns, rotation, infall, outflow, carry information about what gravity is demanding. The goal is to separate what is caused by visible mass, what is caused by a central point mass, and what would require additional unseen mass. That separation is hard, and it is also the point. The galactic center is not a simplified textbook diagram, so any theory that survives here earns respect. In standard cosmology, dark matter density rises toward the center in many halo models, though the inner slope can vary. Yet the baryonic environment is violent, and feedback from stars and supernovae can reshape distributions. Some modified gravity models claim the opposite trend, with reduced need for dark matter-like effects where acceleration is high. The galactic center is where these predictions diverge most sharply, because acceleration is enormous and the environment is dense. If a theory predicts a change in behavior, this is where the change should be easiest to catch. The irony is that easiest still requires decades of data and exquisite precision. This is not a claim that Sagittarius A will overthrow dark matter tomorrow, and it is not a promise of revolution on a schedule. It is a claim that the center is one of the few places where gravity is both strong and measurable in detail. The same stellar orbit data that proved the black hole's mass can also constrain exotic alternatives. The stakes are high because the outcome touches the foundation of cosmology, and foundations matter when you build upward. If gravity behaves exactly as general relativity predicts, that is a victory for Einstein in one of the harshest arenas. If subtle deviations appear, they would be a clue that our map is incomplete. The second paradigm pressure point is black hole growth in the early universe, and Webb has sharpened the tension. JWST has found very massive black holes at surprisingly early cosmic times, when the universe is only a few 100 million years old. Their masses strain simple growth stories that rely on slow, steady accretion from small seeds. To grow that fast, a black hole needs either a big head start or a faster engine, and both options are uncomfortable. One route is heavy seeds from direct collapse, where a large gas cloud forms a black hole without first becoming many stars. Another route is sustained super-Eddington accretion, where inflow temporarily exceeds the classical radiation pressure limit. Another route is rapid, repeated growth episodes triggered by chaotic inflow and efficient angular momentum loss. That phrase can sound abstract, so make it concrete. Gas must shed its spin to fall inward, and shedding spin is difficult unless something, turbulence, magnetic stresses, or gravitational torques, acts like a brake. This is where Sagittarius A becomes relevant without being a direct analogue, and the distinction matters. Today it is low luminosity and underfed, a supermassive black hole on a sparse diet. It is not a quasar, and it is not swallowing a galaxy's worth of gas, but the microphysics of its plasma can scale, and the mechanisms that convert magnetic energy into particle energy do not care about our era. A reconnection event near a small black hole and one near a large black hole follow the same electrodynamic rules. The difference is the size of the stage and the amount of fuel. Webb's flares point to magnetic reconnection in a hot magnetized flow, and that is not just a buzzword. In a radiatively inefficient accretion flow, much of the energy stays in the plasma rather than shining away. The gas is tenuous, the ions can be hotter than the electrons, and magnetic fields can dominate local dynamics. Reconnection is a fast way to rearrange magnetic topology and release stored energy, and fast here means fast compared to orbital times. It accelerates electrons, changes emission, and can launch outflows that carry energy outward. Those outflows can interact with surrounding gas, shaping the environment that will later feed the black hole. In a young galaxy with far more fuel, the same reconnection physics could help drive intermittent, high-efficiency accretion states. Intermittent matters because it changes the growth curve. A black hole that grows in bursts can reach a large mass even if it spends time in quieter phases. The connection is not that reconnection directly adds mass, because light is not food. The connection is that reconnection and turbulence can regulate angular momentum transport and heating. They can create bursts of inflow by changing magnetic stresses, and they can also create outflows that remove energy and redistribute matter. That redistribution shapes when accretion becomes runaway, and when it stalls, and those switches are the difference between a dim nucleus and a quasar. In other words, Sagittarius A may be a nearby microphysical ingredient in a cosmic growth recipe. Early quasars may have grown through episodes, not smooth feeding, and episodes require triggers. Triggers often come from magnetic and turbulent instabilities, because instabilities are nature's way of changing regimes. Webb is watching those instabilities in real time, in the only supermassive black hole we can monitor this closely. The value is not drama, but calibration. We have to state the limits clearly, because a good mystery still respects boundaries. Sagittarius A is quiet compared to active galactic nuclei. Its accretion rate is tiny relative to its mass, and its luminosity is a faint ember compared to a quasar's blaze. Using it as a model for early quasars requires caution, because the environment is different and the feeding rate is different. Yet the laboratory value is unmatched, and that is why we keep returning to it. We know its mass from stellar dynamics, and we know its distance and environment with unusual confidence. We can coordinate multi-wavelength campaigns that are impossible for distant galaxies, and we can do so repeatedly. We can watch the same object flare again and again, and we can compare infrared, radio and X-ray behavior in the same night. We can test general relativistic magnetohydrodynamic models against time-resolved data, not just time-averaged images. Time is the lever that makes this chapter a climax, because variability is not just drama. Variability is a ruler, and it measures the size of the emitting region with ruthless logic. If brightness changes in minutes, the emitting region cannot be larger than light minutes across, because information cannot travel faster than light. Light travel time sets a hard upper bound on size, and that bound is independent of our feelings about the data. For a 4 million solar mass black hole, minutes correspond to only a few gravitational radii. That places the action near the event horizon, where space-time is steep and orbital periods are short. It means the flares are not distant fireworks in the central molecular zone. They are horizon-scale plasma events, happening in a region comparable to the size of our solar system and often smaller. The galaxy's centre is far away, yet the physics is intimate. Timing also carries more subtle information, and Webb's strength is that it can measure timing with precision while separating wavelengths. If a flare peaks first at shorter infrared wavelengths, and later at longer wavelengths, that lag constrains cooling and expansion. The data become a movie of energy moving through a plasma. Synchrotron cooling times depend on magnetic field strength and particle energies, and the dependence is specific. Higher energy electrons radiate faster, so they fade sooner, and that can create a wavelength-dependent delay. Expansion changes optical depth and shifts emission to longer wavelengths, as the plasma blob becomes more transparent. When Webb sees a lead at about 2.1 microns and a lag at about 4.8 microns, it narrows the model space. It favours a picture where energetic electrons cool, and the emission evolves as the plasma changes. It challenges models that rely on a single stable orbiting hotspot, because the evolution looks more like a cascade than a clock. It pushes us toward turbulence and reconnection as the dominant drivers, because turbulence naturally produces intermittent bursts. In a turbulent flow, energy is transferred across scales, and small regions can become temporarily extreme. Reconnection then acts as a release valve, converting stored field energy into radiation. Timing can also connect to other bands, and the connections are as important as the absences. If near-infrared flares were always accompanied by X-ray flares, inverse Compton processes would be efficient and common. Inverse Compton scattering is when fast electrons boost lower energy photons into the X-ray regime. Chapter 3 showed that at least some mid-infrared events lacked X-ray counterparts, and that absence is a constraint, not a disappointment. It limits the population of the highest energy electrons, and it limits the density of seed photons available to be boosted. It tells us the flare is not always a single mechanism, and not always the same mechanism. So the real mystery is not a spooky sound, and it is not a secret message hidden in a waveform. The real mystery is why the galactic center behaves like a living engine while remaining dim overall. It flickers constantly, yet it does not ignite into a sustained active state. It sits on the edge between starvation and activity, and Webb is measuring that edge with a kind of calm insistence. Every flare is a probe of conditions near the horizon. Every quiet interval is also data, because it tells us what the system does when it is not erupting. This is where the earlier chapters converge, and the convergence is not metaphorical. Sagittarius A flickers on minute scales, and that flicker is the inner engine's heartbeat. Sagittarius C shows a filamentary maze where magnetic structure and shocks compete, and that maze is the wiring in the larger machine. ALMA maps shock highways and space tornadoes that churn the central molecular zone and regulate inflow, and those flows are the fuel lines. The center is not one object, it is a coupled system, and coupling means feedback. The coupled system is also where threat narratives fail, because the physics does not care about our fear. A flare is not a doomsday signal because distance and geometry protect us. The energy is real, but it dissipates across 26,000 light-years, spreading thin like light from a match across an ocean. The risk is not immediate harm, and it is not a sudden galactic catastrophe. The risk is misunderstanding, because misunderstanding turns science into superstition, and superstition is a kind of intellectual darkness. When people believe the universe is sending threats, they stop asking what the universe is actually doing. Yet the system does carry a different kind of unease, and it is more mature than panic. If the center can change states, it can change on timescales that matter to a galaxy. The Milky Way has likely had active episodes in the past, hinted by large-scale structures like the Fermi bubbles. Those bubbles are vast lobes of high-energy emission extending above and below the galactic plane, like scars or smoke plumes. They imply that energy was injected from the center in the relatively recent past, though recent still means millions of years. Episodes like that require changes in feeding and feedback, and the central molecular zone is the control panel. So we ask the central question again, now sharpened by everything we have removed and everything we have learned. What did JWST actually reveal about Sagittarius A and the galactic center? Did it reveal a threat or a clue about how black holes and galaxies evolve? The answer is that it revealed a clue, and the clue is variability anchored in magnetic turbulence. It revealed that the emission is not steady, and not simply periodic, but structured in bursts. It revealed lags that point to cooling and expansion, and it revealed a system that is active even when it is faint. The clickbait sound is a distraction, but it is also a doorway, and doorways can be used well. It brings people to the edge of a real mystery, and then the science can take over. Why does a supermassive black hole flicker like this? And why does it flicker so often? How does magnetic energy turn into light? And how does that conversion depend on field strength and plasma density? How does chaotic inflow from the central molecular zone translate into horizon-scale flares, and what regulates the handoff? These are not spooky questions, but they are deep. And then the cosmological stakes return, because local physics becomes a template for distant interpretation. If we can decode the flare physics here, we can better interpret the early universe's black holes. We can test whether growth was episodic and magnetically regulated, rather than smooth and predictable. We can refine the conditions under which a nucleus transitions from dim to quasi-bright, and we can identify what trigger might mean in plasma terms. Does the trigger require a threshold in magnetic flux? Does it require a change in inflow geometry? Does it require turbulence to cross a critical intensity? Gravity returns as the deeper foundation under all of it, because gravity sets the stage on which plasma performs. Stellar orbits near Sagittarius A already validate general relativity in a strong field regime, and they do so with numbers, not slogans. Future precision can test for subtle deviations and constrain extended mass components, tightening the net around alternatives. The galactic center becomes a proving ground where dark matter assumptions and gravity alternatives face data, and where failure is informative. If a model cannot survive the center, it may still be useful elsewhere, but it cannot claim universality. The center is not the whole universe, yet it is a harsh judge. In this chapter, the terrifying anomaly changes shape, and the change is the point of the arc. It is not a supernatural warning and not an impossible sound, because the universe does not need to whisper to be dangerous. It is the realization that the Milky Way's heart is a turbulent, magnetized engine that we can watch in real time. The terror is not doom. The terror is scale and indifference, and the beauty is that it is measurable, counted in photons, plotted in curves, constrained by timing. The center does not care that we listen, yet it still leaves evidence we can read. Now the narrative turns towards synthesis and resolution, because the pieces are on the table. We have the flicker at the horizon, the maze in Sagittarius C, and the tornadoes in the central molecular zone. We have the false sound stripped away, and the real physics exposed. The final act must answer what Webb truly revealed, and what it implies for our place in the cosmos and the future behavior of our galaxy's center. It must connect the minute-scale flare to the million-year bubble, and the local plasma to the early universe's giants. It must show how a quiet black hole can still be a loud teacher. We return to the core question with no filters, and with no need for horror effects. What did JWST truly reveal, and what does it imply for the future behavior of our galaxy's center? The next chapter brings every thread into one coherent picture, and it ends the hype with evidence. Sagittarius A flickers, Sagittarius C tangles, the central molecular zone's tornadoes churn. Now we assemble the engine and we ask what it is building across cosmic time. We return to the central question with the hype stripped away and the data intact. JWST did not reveal a doomsday signal from Sagittarius A. It revealed persistent, chaotic infrared variability near the event horizon, driven by magnetic reconnection in a turbulent flow. That distinction matters because the internet loves a single dramatic trigger, while nature prefers messy baselines. Webb's cameras did not catch a one-time scream from the centre. They caught a restless, ongoing flicker that refuses to sit still. The terrifying anomaly is not silence. The anomaly is continuous activity from a black hole labelled quiet, a label inherited from decades of low average brightness. Webb's long, uninterrupted timing showed flicker as a baseline state, not a rare exception. In the images we imagine, the galactic centre is a dark mouth with a faint ember at its edge. Then the ember jitters, brightening, dimming and brightening again like a fire fed by gusts. The light is not a message, yet it is information. Minutes matter because minutes confine the emitting region to a few gravitational radii. If the brightness changes within tens of minutes, the source cannot be a giant structure. Causality sets a hard limit, because no signal can reorganize faster than light can cross the region. Near Sagittarius A, a gravitational radius is not an abstract unit. It is a real scale set by mass, and Sextile carries about 4 million suns. The event horizon is small in astronomical terms, yet it dominates everything nearby. In a magnetized, underfed accretion flow, low-level flaring is expected. The gas density is low, the plasma is hot, and collisions are too rare to keep electrons and ions in perfect thermal lockstep. In plain language, the flow is thin, violent, and electrically alive. Fields twist as plasma spirals inward and stresses build faster than the gas can settle. Differential rotation winds magnetic lines into tight coils, and turbulence tangles them into knots. When the topology can no longer hold, the field snaps and reconnects. Reconnection releases stored magnetic energy into electrons that radiate synchrotron light. Those electrons spiral around field lines at near relativistic speeds, and their curved paths shed infrared photons. The light curve becomes a readout of plasma physics, not a coded warning. This is not a new idea, and that history is part of the story. For years, telescopes saw occasional near-infrared flashes from Escaré and argued over their cause. Some models favoured orbiting hotspots, while others favoured turbulence and reconnection. JWST's timing constraints are a milestone because they reduce guesswork. Webb can stare without blinking, and that continuous attention is rare in space astronomy. It turns a few dramatic points into a dense time series that can be tested. Multi-band lags and flare shapes narrow the space of viable GRMHD models. If one wavelength consistently leads another, the emitting electrons must cool or evolve in a specific way. If the flare rises sharply and decays slowly, that asymmetry also carries a signature. They favour stochastic turbulence over a single stable hotspot clocking perfect orbits. A hotspot model predicts a kind of metronome, with periodicity tied to orbital motion near the innermost stable circular orbit. Webb instead sees a regularity that looks like a storm, not a clock. They show the inner flow is dynamic even when the total luminosity stays small. That is a subtle lesson, because brightness is not the same as calm. A system can be dim and still churn violently if most energy stays trapped in particles and fields. The missing X-rays become part of the resolution, not a missing piece. A mid-infrared flare without an X-ray counterpart argues against a global ignition sequence. It supports localized, limited reconnection events that do not create a strong Comptonizing corona. In many black hole systems, strong X-rays signal a population of very energetic electrons. Those electrons upscatter lower energy photons through inverse Compton processes, pushing infrared or optical light into the X-ray band. When X-rays fail to appear, the electron distribution is constrained. That absence reassures because it implies no rapid transition toward quasar-like power. A quasar phase would require a dramatic increase in accretion rate and radiative efficiency. Webb's flares look like sparks in a thin plasma, not the first blaze of a feeding frenzy. None of this indicates imminent danger to Earth or the solar system. Distance dilutes energy across 26,000 light-years before it reaches us. Even a large flare would spread over a sphere so vast that the flux at Earth becomes negligible. Geometry and the interstellar medium further reduce any direct impact. Dust and gas between us and the centre absorb and scatter radiation, especially at shorter wavelengths, and any jet-like outflow, if present, is not aimed at us. The threat narrative collapses when you compute flux, timescale, and direction. The numbers are not ambiguous, and they do not bend for drama. What remains is wonder, sharpened by the fact that the centre changes on human timescales. Once the sound myth is stripped away, a deeper tension appears. The galactic centre looks contradictory because it is a coupled ecosystem, not a single object. The black hole's flicker is linked to how gas is stirred, delayed, and delivered on larger scales. To see that ecosystem, widen the frame from the horizon to the central molecular zone. The CMZ is a ring-like region packed with dense clouds, warm dust, and magnetic structure. It is a reservoir that could feed both stars and the black hole, yet it hesitates. ALMA's CMZ kinematics provide the supply chain context for Webb's Minute-scale drama. In radio and submillimeter light, ALMA traces cold molecular gas through spectral lines, then converts Doppler shifts into motion. The result is not a still photograph, but a map of flow. Shock highways form where bar-driven streams crowd and collide, converting ordered motion into turbulence. The Milky Way's central bar funnels gas inward along elongated orbits, and the streams meet at intersections. At those junctions, shocks heat the gas and stir it like a spoon. Space tornadoes mark strong shear and vorticity, not stable cyclones, and they reshape where gas can linger. They are signatures of rotating, twisting motion in the gas, sometimes produced by cloud-cloud interactions and tidal forces. The phrase is poetic, but the physics is real. These processes regulate angular momentum loss, which decides whether gas drifts inward or recycles outward. Gas must shed angular momentum to fall toward the black hole, and turbulence can either help or hinder that loss. In effect, the CMZ is both a funnel and a filter. The visuals here are almost architectural. You can imagine luminous filaments and knots laid over a dark background, with arrows tracing flows that bend around the centre. Some streams converge, some peel away, and some stall in eddies that last longer than a human lifetime. JWST's broader galactic centre imaging adds a second challenge to simple expectations. In Sagittarius C, filamentary magnetic structures and heated interfaces appear where dense gas should form stars efficiently. Instead, the region looks threaded and tense, as if the medium is being held in place. Instead, turbulence, shocks, and magnetic tension keep much of that gas dynamically hot. Hot here does not always mean high temperature in the everyday sense. It often means high internal motion, where random velocities act like pressure against collapse. The core is dense yet inefficient at making stars, and the inefficiency is a clue. In many parts of the galaxy, dense gas correlates with star formation almost by default. In the CMZ, density alone is not enough, and that breaks a comfortable rule of thumb. Magnetic fields are not just decorations in these images. They store energy, transmit stresses, and guide charged particles along preferred directions. When a cloud tries to collapse, magnetic tension can resist, redirecting motion into long filaments instead of compact cores. Put the pieces together and the contradiction becomes a blueprint. Shocks compress gas while simultaneously injecting turbulence that resists collapse. The same collision that piles material into a ridge can also shake it so violently that gravity struggles to finish the job. Magnetic fields guide compression into filaments and sheets, limiting isotropic fragmentation into bound cores. Collapse becomes anisotropic, channeled along field lines and halted across them. The result can be spectacular structure with surprisingly little starbirth. Feedback and shear keep resetting clouds before they can finish the star formation sequence. Stellar winds, supernova remnants, and tidal forces all disturb the gas, and the bar's dynamics keep it moving. A cloud may begin to collapse, then get torn, heated, or shocked back into disorder. This same regulation helps explain why Sagittarius A is active yet dim. The CMZ can hold a large reservoir while delivering only a small, intermittent fraction inward. Feeding a black hole is not about having gas nearby, but about delivering it with the right angular momentum and thermodynamics. Much of the inflow becomes a radiatively inefficient plasma that stores energy in ions and fields. In such flows, ions can carry most of the heat while electrons radiate less efficiently. Energy can also be carried away by winds, leaving less to shine near the horizon. Outflows and heating reduce the mass that reaches the horizon, keeping the black hole underfed. Some gas is blown back out by pressure gradients and magnetic forces. Some is heated so strongly that it puffs up, becoming harder to funnel inward. The updated model of the Milky Way's core is therefore not a sleeping monster. It is a throttled engine with a turbulent intake and magnetic valves. The inner accretion flow flickers continuously, because the supply arrives in clumps and the fields are always rearranging. The outer environment looks sculpted because shocks and magnetism keep drawing new boundaries. Filaments trace invisible field lines, and cavities hint at past bursts of energy. The center is not static scenery, but a landscape under constant revision. This is where the story widens to cosmology without overpromising. Magnetic burst-driven variability is a microphysical ingredient that can scale to other black holes. The same reconnection physics that makes a small flare here can, under heavier feeding, power larger episodes elsewhere. In the early universe, higher gas fractions and stronger inflows could push similar physics into brighter, longer growth episodes. Young galaxies were richer in cold gas, and mergers were more common. If the throttle opens wider, the same engine can roar. Intermittent accretion may help explain rapid black hole growth without requiring steady, perfectly tuned feeding. If black holes grow in bursts, they can reach large masses quickly, even when average conditions look insufficient. That possibility changes how we interpret early quasars. The CMZ star formation suppression mechanisms also travel outward in relevance. High redshift galaxies often show extreme gas densities and turbulent conditions. If dense gas can be inefficient at forming stars in our own center, it can be inefficient in distant starbursts too. That caution changes how we infer star formation rates, feedback, and duty cycles from unresolved light. When a galaxy is a single pixel, we rely on calibrations that assume familiar relationships. The Milky Way's center warns that those relationships can bend under extreme conditions. The galactic center becomes a calibration target for interpreting the young cosmos. Here we can separate turbulence from collapse, and reconnection from global state changes with multi-wavelength timing. There we often see only integrated brightness and broad spectral features. The Milky Way teaches us what those distant averages might be hiding. A smooth light curve can conceal violent microphysics, and a bright line can hide suppressed star formation. The question becomes unavoidable. What else are we averaging away? Future tests must be coordinated because the engine is multiband by nature. JWST and ALMA together can track how infrared flares relate to radio variability and gas conditions. If a flare begins in hot electrons, its signature should ripple outward in frequency and time. X-ray telescopes can confirm when inverse Compton processes turn on and when they stay suppressed. A rare event with a strong X-ray counterpart would signal a different electron population or geometry. A continued absence would strengthen the localized reconnection picture. Polarization mapping can measure magnetic geometry changes during flares and across filaments. Polarized light carries the imprint of ordered magnetic fields, and changes in polarization angle can reveal field rearrangement. In effect, polarization turns invisible structure into measurable motion. Improved orbit tracking of stars near Sagittarius A remains a second pillar of confirmation. For decades, astronomers have watched stars like S2 trace tight ellipses, using their paths as test particles in a relativistic potential. Each orbit is a slow experiment run by gravity itself. Better astrometry tightens constraints on relativistic precession and any extended mass component. General relativity predicts that the orbit's closest approach should rotate over time, and that effect has now been detected. The next step is measuring it more precisely and for more stars. Those measurements can discriminate between a pure point mass potential and additional distributed matter. A cluster of dark objects, or a dark matter cusp, would subtly alter the gravitational field. The deviations would be small, but they would accumulate in the data. They also test whether gravity deviates subtly from general relativity in the strongest accessible field. The galactic center is not a black hole merger, but it is the best strong field laboratory we can watch continuously. The question is not philosophical, it is measurable. This is where dark matter and modified gravity claims face a hard arena. Standard dark matter models predict certain central distributions, though baryonic feedback can reshape them. Some modified gravity ideas predict reduced dark matter-like effects in high-acceleration regimes. Precision stellar dynamics near Escaré can narrow which story survives contact with reality. If the potential matches a point mass plus known stars that constrains additional components. If it does not, the discrepancy must be explained with disciplined physics, not slogans. Next-generation instruments will push the boundary from suggestive to decisive. Higher cadence infrared monitoring will catch smaller flares and measure lag distributions. Better sub-millimeter polarization will reveal whether magnetic flux accumulates or disperses before major events. Deeper X-ray coverage will test whether rare flares ever produce a true high-energy counterpart. If they do, we will learn when the system briefly resembles more luminous black holes. If they do not, the dimness becomes an even stronger statement about the flow's structure. We cannot send Voyager 2 to the event horizon, and we cannot launch SpaceX missions into a black hole. The journey here is made by photons, timing, spectra, and polarization, stitched into a physical narrative. Remote sensing becomes intimacy when the object changes on human timescales. In the mind's eye, that intimacy looks like a control room built from light. A jagged infrared curve scrolls across a screen, while radio maps reveal swirling gas lanes. Over it all, polarization vectors tilt and rotate, hinting at magnetic fields snapping into new shapes. The conclusion is not apocalypse. It is a blueprint for how galaxies regulate their cores through turbulence, shocks, and magnetic fields. Webb showed that Escaré is continuously active, and that activity is expected in a magnetized accretion flow. ALMA and JWST together showed a center that is dense, chaotic, and self-throttling. The CMZ stores fuel, but turbulence and magnetism ration its delivery. Sagittarius C displays structure that looks ready to form stars, yet remains stubbornly restrained. The terrifying part is not that Sagittarius A is coming for us. The terrifying part is that the cosmos is stranger than our equations, and JWST just opened a door we cannot close. When we look into that door, we do not see an ending. We see a deeper set of rules, still being written. Across 26,000 light-years of dust, the story kept narrowing, from myths and metaphors into measurements, until the Milky Way's center became readable. Webb didn't hear a warning, it watched calibrated infrared light curves and spectra,